The second presentation is seismicity on the territory of Bulgaria and surroundings recorded by NOTSI for the period 2017-2019. Presenter is Dragomir Dragomirov. Unfortunately, I don't see Dragomir.
Господин Гаджев, чувате ли?
He's here.
Да, след...
Okay.
След 30 секунди е включвам ефир.
Dragomir, do you hear me?
Да, аз изключвам сега звука. Аз изключвам звука. Изключвам звука.
Dragomir. Dragomir, do you hear me?
Can you hear me? Hello?
Yes.
Oh,
Yes, Dragomir, you can start your presentation.
fine. Okay, thank you. So, my presentation is going to be on the seismicity on the territory of Bulgaria and the surroundings, recorded by NOTSI for the period of 2017 to 2019. The Balkan Peninsula is one of the active regions in the Alpine Himalayan belt. High activity is observed in western Turkey, Greece, Bulgaria, northern Macedonia, Albania, and the Branch region of Romania. Bulgaria is an earthquake-prone country historically, and during the period of 1921 to 1928, there were 5 strong earthquakes with magnitude of 7 or larger, which occurred on the territory. Impacted territory in Bulgaria. Had the earthquakes. Here I have shown earthquakes from the earthquakes from Japan in 1928 with magnitude of 7.1, which had a lot of deaths and destruction, as well as the one from 1986 with magnitude of 5.6. And another earthquakes that have impact on the territory of Bulgaria are the ones in the region of Branch, especially the one in 1977, which I'm sure some people may still remember. And now let's talk about the period enough with historic data. The period we're studying is from 2017 to 2019. And it contains general information and analysis of the data about the seismic events of that period. Seismic data is gathered in real time by 26 Bulgarian stations and a number of stations from neighboring countries, which help increase the hypocentral accuracy. During that period, 411 of all registered earthquakes were on the territory of Bulgaria and the surroundings. And our region is, as you can see on the map, is outlined by 41 degrees to 4.5 degrees in latitude and 22 to 29 degrees in longitude. During the year of 2017, we have recorded 114 earthquakes. During 2018, we have recorded 168 earthquakes. And during 2019, we have recorded 129 earthquakes. The number of events with a magnitude interval of between 2.5 and 3 is 305. Between 3.1 and 3.5 is 72. Between 3.6 and 4 it's 22, and between 4.1 and 4.5 it's 10. And between 4.6 and 5 we have only 2 events. This distribution shows that the number of events decreases with the increase of magnitude. Now, this is a magnitude distribution throughout the years, and each color represents a different year. 2017 is represented by blue, 2018 is represented by orange, and gray represents 2019. we can see that there is a spike in activity in 2018 in each uh, in each magnitude interval, and we're gonna see later that is because of increase in activity uh, in the southwestern region of Bulgaria because of an earthquake that of magnitude 5 that occurred around the border of Bulgaria and Macedonia. But despite that spike in activity, uh, we can see that the overall characteristic distribution in the different intervals uh, has been kept, has been consistent. This graph shows that the data fit well with the theoretical expectations, meaning that likely all incoming earthquakes have been detected by the network. Here you can see the spike in activity that I was talking about earlier. This is a distribution of earthquakes, uh, number of earthquakes compared to uh, their, their respective coordinates, and you can see the southwestern part of Bulgaria has spike in activity because of that earthquake. During the study period, 63 earthquakes in total were felt on the territory area from local and regional sources. The strongest being the earthquake in Tirana, Albania, with a magnitude of 6.4. And throughout the study period, earthquakes occurred generated in seismogenic zones in the territory of Bulgaria with maximum intensity in the epicentral zone of 5. Maximum intensity was 5. And these are the 3 earthquakes which generated that. We can see that the distribution of depth is it's very characteristic for the territory area. It varies. The largest amount, the largest number of earthquakes is between 5 kilometers and 20 kilometers, and we can see that on this graph and better on this graph. As you can see, the, the largest amount is between 5 and 20 kilometers, and uh, in, in that interval we can see another interval between 10 and 15 where most of the earthquakes. This is a distribution of the number of earthquakes throughout the months from the beginning of 2017 until the end of 2019. And we can see that uh, in, in January of 2019, February as well, we have respectively 43 and 32 events happened that month. And that is, of course, because of the earthquake, which occurred uh, close to the border of Bulgaria in Greece, close to the border of Bulgaria with a magnitude of 5. And all of these are foreshocks and aftershocks of that event. We can see another spike in activity in February of 2019. and that's why activity would contribute to activity in the southwestern part of the area and the east part of Black Sea, just off the coast of Gas. And that's it. Thank you for the attention.
Thank you, Dragomir.
Questions?
Unfortunately, the sound quality was not so good, but nevertheless, if someone have any question,
Yeah, I'm sorry for the sound quality. I thought the microphone was working.
okay. Thank you, Dragomir. The next presentation is seismological analysis of the 2006 Kırjali earthquake. The presenter is Plamena Raikova. Plamena, you have the floor, please.
Hi, do you hear me?
Yes.
Okay. Hi everyone, my name is Plamena Raikova from National Institute of Geophysics, Geodesy and Geography, Bulgarian Academy of Science. The topic of my presentation is seismological analysis of the 2006 Kırjali earthquake. Studying of the space-temporal time distribution of earthquakes is very important for understanding the physics of the earthquake generation process. The 2006 Kırjali earthquake with moment magnitude 4.7 was followed by an intensive aftershock activity. The space and temporal clustering of aftershock is a dominant non-random element of the seismicity. So when the clusters are removed, the remaining activity can be modeled as first approximation of some process. Aftershocks are defined as seismicity above the background activity following a main shock. Aftershock occur after the main event and their frequency decays over time, typically following a pattern known as the Morris law. The manifold purpose of the study is first to determine the space and temporal pattern of aftershock distribution in the epicentral zone, the 2006 Kırjali earthquake, then to test the different statistical models for aftershock occurrence based on the transformation of the time scale to frequency linear time scale tau. Finally, the criteria is used to select the best statistical model for aftershock occurrence. Another part of this study is technical analysis of seismic waves. This analysis is one of the most important original information for the earthquake sources. In the study, spectrography and phase waves for earthquakes from the seismic cluster main event aftershocks of the 2006 earthquake are generated. Earthquake parameters are estimated applying a Brun model. The frequency of aftershock at time is well represented by the modified Mori formula, which is presented here, where the T is the elapsed time since the occurrence of the main shock, and the Kp and C are the constant parameters. The most important parameter is P, which characterizes the decay of the aftershock sequence. On the assumption that the aftershocks are distributed as a non-stationary Poisson process, it's proposed to use the maximum likelihood method for estimating the parameters in modified Mori formula. The frequency linear time can be defined as this. where the time scale is used for testing the goodness of fit between the aftershock occurrence and the selected model. Also, a linear dependence between the observed cumulative number and cumulative number aftershock and frequency linear time scale should be observed in appropriate model has been selected. To select which model is the best fit to the observation, we use the Chi criteria. This is a measure of which model most frequently reproduce features similar to the given observation and defined with the next equation. A model with a smaller value of a Chi criteria is considered to be a better fit to the observation. In this study, spectra of P and S wave for the earthquakes from the seismic cluster main event and aftershock of 2006 earthquake are generated. The parameter like seismic moment, source radius, and stress drop are estimated applying a Bloom model. This model has been used extensively and it has been shown that it gives a good agreement with the observation from many different tectonic regions and for a large range of magnitude. The seismic moment is the most objective static measure of the earthquake size. The solar static moment is defined by next equation, where mu is the shear model of the rocks, S is the area of the rupture along the geological fault, and D is the average slip. The stress drop is the average difference between initial and final stress along the fault after an earthquake. These parameters can be defined with next equation, where M is the seismic moment, L is the fault radius. The source radius can be defined as well with next equation, where L is whereas beta is the velocity of P and S wave, F is frequency, and K is constant. In this study, spectra are generated on the base of the records from station at distance less than 200 kilometers. Some results in the figure here are presented phase distribution of aftershock activity after the main event with moment magnitude 4.7. This earthquake is located near the city of Kırgılı. Figures show some following characteristics, like that the main shock and aftershock activity are clustering in area that is not associated with the defined fault structure. A well-expressed tendency of aftershock area expansion in time and with decrease of magnitude is observed. Also, the aftershocks with magnitude less than 3 are dispersed in space and spare over area. In this study, is analyzed the aftershock sequence from 0 to 50 days after the main event. The time interval is the calculated value of the greatest ellipse time since the occurrence of the main shock using this equation. In this study, two sets of data is analyzed. First includes all aftershock, and the second includes all events with magnitude bigger or equal than 2, located inside the area of interest. The parameters K, P, and C in the modified Mori formula are estimated using the maximum likelihood method, and the estimated value of this parameter is presented in the table here. In the figure are presented frequency time distribution of earthquake for two different data sets. The cumulative number of events is plotted against the frequency linearist time using the estimated parameters K, P, and C. The observed distribution is compared to the theoretical distribution based on the selected model. The results from the figure here and from the table in previous slide show that the model with one ordinary aftershock sequence without threshold magnitude described best the aftershock sequence of the 2006 earthquake. Figure showed that a nearly linear trend of aftershock decay continues up to 53 days. About these days after the main shock, the cumulative number of aftershocks increased rapidly with time scale tau, showing significant deviation from the prior trend. Therefore, this change in slope could be treated as a transition from aftershock activity to the background seismicity. The predicted duration of aftershock activity is 42 days, which is approximately the same with the observed duration. In the present study, 96 digital records from 6 earthquakes are analyzed. The source parameters are estimated for the main event of this sequence, so with moment magnitude 4.7, sorry, and for the 5 of the aftershock with moment magnitude in range 3.3, 3.7. In the figure here is presented spectra for the main event based on the records of the three of the nearest stations. The first spectra is for the Z component, and other two is for the horizontal component. In table here are shown parameters of the events of the 2006 seismic cluster for the main event and for the 5 of the strongest aftershock. In the next figure are presented displacement spectra for P and S wave for the 5 of the strongest aftershocks. In the figure are presented displacement spectra based on the records of the nearest station. Every row here presented displacement spectra for P and for S waves for one of the nearest station for the one aftershock. As a result, we can say that the result for the main event is with the expected range for the moderate earthquake about 65 bars, because the expected range for the moderate earthquake is from 10 to 100 bars. The strongest aftershocks are characterized with the lower than the main event stress drop value. The stress drops for the aftershock is between 8 to 64 bars. Source radius for the main event is approximately 1.7 kilometers. The results for the source radius for the aftershocks are from 0.2 to 0.5 kilometers. The seismic moment for the aftershocks are in range 1.5 10 to the 13 degree to 3.5 10 to the 14 degree. For the corresponding moment magnitude, which is estimated by displacement spectra, in the interval to 2.7 to 3.5. As a conclusion, we can say that the spatial distribution of earthquakes is not uniform before and after the main shock. Larger events tend to be more clustered than smaller ones. Temporal distribution of events in aftershock sequence is well described by the Modi formula. The p-value estimated for the aftershock sequence is the middle of the p-value range obtained for the aftershock sequence in Bulgarian surroundings. Transition of aftershock activity to background is observed about 53 days after the main shock. The estimated stress drop value for the main event is within the expected range for moderate earthquake. The strongest aftershocks are characterized with lower than the main event stress drop value. We want to thank for support from this project, and thank you for your attention.
Thank you, Plamena. I would like to say that this earthquake occurred just after modernization of the whole Bulgarian network, and all stations became digital, so we can believe the results. Okay, I see here that after the session there are QA sessions, so if someone has questions in the interval between 12:30 12:45. Okay, the next presentation is seismicity patterns associated with earthquakes on the Balkan Peninsula. Presenter is Emil Vinakov. Emil, please, you have the floor.
Da? Astăzi sunt.
MOTC.
Okay.
Hello, I am Emil Oinakov and I will present to you Seismic Station Site Effect for the National Operative Telemetric System for Seismological Information, NOTSI, network calculated on the basis of microseismic noise. Introduction. One of the important indicators for estimating tensions in the Earth's crust is the level of released tensions, which can be determined by analyzing the dynamic parameters of the earthquakes. An important element in the calculation of the dynamic parameters is the transition from station spectrum to spectrum in the epicon tray, by which the angular frequency, F0, and the spectral density, omega 0, are determined. Such transition must take into account the influence of the environment and the site effect below the station, amplification, along the path of the seismic beam. There are various methods for determining site effects, described in various articles. Lemzikov, 2010, Makagan, Sikova, 1994, Panteleyeva, 2013. One of the most promising and economical methods for determining site effect under the station is based on the analysis of seismic noise using the Nakamura method. In order to minimize the influence of the upper layer under the stations on the seismic record, during the installation of the Nazi network stations, the places where the rocks come to the surface were selected. Seismic stations. At present, the National Seismic Network, Nazi, established in 1980, is a major part of NIGBES. The network was upgraded in 2005 and consists of 17 seismic stations and 2 local networks. The main task of the network is to monitor the seismicity realized on the territory of Bulgaria and the surrounding lands. Nazi is currently a world-class digital network that determines real-time earthquake parameters. The network provides reliable seismological information related to seismic risk reduction, both for the expansion of the research activities and for the work of the institutions. The methodology for analysis, assessment, and mapping of the seismic risk in Bulgaria and the new assessment of seismic hazard for Bulgaria created in recent years, are based on the high-quality information from the Nazi. The figure shows the location of the 11 seismic stations from the Nazi network, the data from which were used in the study. Nakamura method. At the center of the method is the notion that the influence of the thin layer, not a large layer of the Earth's crust, just below the seismic station, on the studied object, greatly amplifies the transverse waves, S waves, and practically does not change the longitudinal, P waves. Then the ratio of the spectral characteristics of the two horizontal components to the spectrum of the vertical component will characterize the so-called preliminary function, which depends on the thin layer below the object under consideration. As is known, the seismic sensors measure movements of the Earth's crust in three directions: north-south, N, west-east, E, and vertically, Z. Essentially, the method determines the ratio of the spectrum of the horizontal components, H, to the spectrum of the vertical component, V. The H component is calculated as the average square of the spectra of the E and N components, and V corresponds to the spectrum of the component Z, Formula 1. Then directly is calculated the H/V ratio with Formula 2. In order to obtain the average characteristic of the ratio for one station, it is necessary to consider N time windows from seismic noise. Thus, for the N interval of the station record, N ratios H/V are calculated, and their average is determined, Formula 3. In the study of seismic noise, the time window, interval, of the recording should be from 30 to 60s, Parola, ETAL, 2004, Picazzi, ETAL, 2008, Nakamura, 1989. The choice depends on the characteristics of the seismic sensor. From the selected section of the record, the linear trend is removed and, to prevent distortions at the ends of the spectrum, is smoothed out with the help of a 5% cosinusoidal window. Then it is smoothed with the help of the Horso-Maka method. Data processing. For each components of the investigated window, N, E, Z. Removing a linear trend. Smoothing the signal using a 5% cosine window. Construction of the spectrum using the FFT for a segment with a length of a multiple of a power of 2, 4096, in the frequency range 0.01-10 Hz. Spectrum smoothing by the Kano and Omachi method with a coefficient characterizing the throughput, B equals 40. For every window. Calculation of the horizontal component of H as the root mean square of the spectra of the components of the E and N components. Calculation of the ratios of the spectra of horizontal, H, to vertical, V, components. For many windows. Calculation of the average of all considered windows. Result. The figures show part of the first group of stations, Krupnik, KKB, Plana, PLN, and Plovdiv, PLD. In general, the H/V spectral curves for the stations in the first group are curves complicated slightly by small amplitude extrema. For some of the curves the level rises in the high frequency range. For seismic station Krupnik resonance frequency F0 is 7.95 Hz and amplitude equals 2.791. For seismic station Plana resonance frequency F0 is 13.11 Hz and amplitude equals 2.291. For seismic station Plovdiv resonance frequency F0 is 1.574 Hz and amplitude equals 1.543. The figures show part of the first group of stations, Precelency, PSN, and Vitasha, VTS. For seismic station precelency resonance frequency F0 is 1.105 Hz and amplitude equals 2.0076. For seismic station Vitasha resonance frequency F0 is 1.496 Hz and amplitude equals 1.145. For some of the curves the level rises in the high frequency range. These types are H/V ratio curves for Karjali, KDZ, and Musimist, MMB, stations. This type of H/V ratio curve is typical for stations located directly at the outcrops of the root rocks of the surface foundation. For seismic station Karjali resonance frequency F0 is 1.105 Hz and amplitude equals 2.0076. For seismic station Musimist resonance frequency F0 is 1.496 Hz and amplitude equals 1.145. Theoretically, for such stations, the H/V spectral curve should be straight parallel to the abscissa with an amplitude of about 1. The obtained H/V spectral curves for the stations in the first group satisfy this condition. For Musimist, Plovdiv, Precelency, and Vitasha stations we can notice smooth low-frequency extremes and for Krupnik medium-frequency stations. Result for the second group station. The second group includes stations Provadia, PRD, Strizica, SZH, Panagurist, PGB, and Tran. For three of the seismic stations, Tran, Strizica, and Provadia, the presence of narrow extremes of the H/V curves localized at frequencies of 4 to 10 Hz is observed. All four seismic stations in the second group are located at the outcrops of the root rocks on the surface, so that the presence of extremes cannot be explained by local soil conditions. The study of fracture zones by the low-frequency microseismic sounding method shows that such extrema are observed close to the areas of high cracking and fragmentation with signs of Pliocene activation. Also, these types of extremes can be caused by the passage of a seismic signal through large structural inhomogeneities. Table shows the calculated station corrections, amplification factor, the resonance frequency F0 and the depth of reference of the most contrasting resonance boundary H, calculated by the formula, for, where, Vs is the transverse wave speed taken from physical constants and modules of some rocks and minerals, Christoskov, 2007, depending on the substrate on which the seismic station is deposited. Conclusion. Side effects have been made using the Nakamura method applied to seismic noise recordings. The resulting side effect for the stations from the Nazi network can be used in the transition from station spectra to the source spectrum. Acknowledgements. This work has been carried out in the framework of the National Science Program Environmental Protection and Reduction of Risks of Adverse Events and Natural Disasters, approved by the resolution of the Council of Ministers No. 577/17.08.2018 and supported by the Ministry of Education and Science, MES, of Bulgaria, Agreement No. 01322/18.12.2019. Thank you for your attention.
Thank you, Emil. This was the last presentation for this session. And now we have time to questions and answers. Please, if anyone has question, please. Okay, you can ask the presenters. Okay, obviously there are no questions, so it's time for coffee break. Thank you.
Hello, my name is Stefania Klein. I'm a researcher at the Institute of Biodiversity and Ecosystem Research of the Bulgarian Academy of Sciences. I'd like to present the results of our study entitled Effect of Organic Matter Loading on Nutrient and Oxygen Fluxes at the Sediment-Water Interface in Different Sedimentary Habitats in Sozopol Bay. Coastal ecosystems located at the interface of land and sea are home to some of the most diverse marine ecosystems with a variety of habitats and biological communities. At the same time, the coastal zone is densely populated and has been for the entire human history. Many often competing human activities are concentrated there. They often result in increased nutrient inputs to the coastal sea from agriculture, industry, coastal cities, transport. The eutrophication resulting from these inputs and consequent deterioration of water quality are still reported worldwide despite legislative and management mitigation measures in recent years. Coastal systems, being the first to receive anthropogenic nutrient inputs, act as a buffer for the open ocean by either retaining and or transforming nutrients or recycling them back into the water column and making them available for primary producers. Hello, my name is Stefania Klein. I'm a researcher at the Institute of Biodiversity and Ecosystem Research of the Bulgarian Academy of Sciences. I'd like to present the results of our study entitled Effect of Organic Matter Loading on Nutrient and Oxygen Fluxes at the Sediment-Water Interface in Different Sedimentary Habitats in Sozopol Bay. Coastal ecosystems located at the interface of land and sea are home to some of the most diverse marine ecosystems with a variety of habitats and biological communities. At the same time, the coastal zone is densely populated and has been for the entire human history. Many often competing human activities are concentrated there. They often result in increased nutrient inputs to the coastal sea from agriculture, industry, coastal cities, transport. The eutrophication resulting from these inputs and consequent deterioration of water quality are still reported worldwide despite legislative and management mitigation measures in recent years. Coastal systems, being the first to receive anthropogenic nutrient inputs, act as a buffer for the open ocean by either retaining and or transforming nutrients or recycling them back into the water column and making them available
If everybody's here, I think we can continue with the session. My name is Dragomir Dragomirov, and I'm going to be moderating this session of natural hazards and risks. As you can probably see, I'm speaking from Emil Oinakov's account because I have had some complications with my system, and me and him are going to be alternating between the microphone, but do not fear, there's a distance of at least 2 meters between us. Okay, we can start. The first presenter is Emil Oinakov, and his topic is going to be seismicity patterns associated with earthquakes on the Balkan Peninsula. Go ahead.
Hi, I'm Emil, and I'll introduce you. Seismicity patterns associated with earthquakes on the Balkan Peninsula. Introduction. There are a lot of studies on the spatial and temporal phenomenon of precursory seismic quiescence, use different approaches to measure, map and evaluate possible episodes of seismic quiescence, example RTL, pi, RI, ZMAP, etc. Some of these studies on the precursors of past earthquakes suggest that particular space-time seismicity patterns, including the phenomenon of precursory quiescence, can be related to the seismotectonic processes that lead to earthquakes. Statistical analysis was performed, which reveals statistical parameters of the seismic setting before the earthquake in the region of Crete, January 4, 2011 with coordinates 26.56 east, 35.64 north, magnitude equals 6.2, depth equals 63 kilometers and T0 equals 13, 29, 10.5 hours of GTM. For this purpose, the spatial and temporal changes in the B value and the value of the Z seismic lull were estimated. In addition to variations in changes in seismic activity and seismic lull, the values of B can also be indicators of an impending earthquake. The spatial variations in the slope value of the repeatability graph, B value, characterize the seismicity in a given region. Tsukakoshi, Shimazaki, 2008. Methodology. Considering the exponential distribution of earthquakes by magnitude, Gutenberg, Richter, 1944, the value of the slope of the recurrence graph is estimated by the method of maximum likelihood, Utsu, 1965, Formula 1. Where mean, average value of magnitude in the sample, min, is the minimum magnitude of the sample and is calculated as min equals MCM/2, where delta m takes into account the rounding of magnitude, and here is selected delta m equals 0.1, Schorlemmer, Weimer, Weiss, 2004, and MC, the magnitude of the completeness of the sample. Formula 2 show the root mean square error of the estimate. In this study, the spatial distribution of the B value was calculated using the ZMAP software, Weimer, 2001, Weimer, Weiss, 1994, using the maximum likelihood methods and the least squared regression method. According to Aki, 1965, the maximum likelihood method gives a more solid estimate than the least squared regression method. The first step in analyzing B values is to determine the magnitude of MC's completeness and its error. MS is defined as the lowest magnitude at which 100% of events in a given space and time are detected. Weimer, Weiss, 2000, Weimer, Weiss, 2002. Values lower than MC are considered heterogeneous and incomplete. In order to identify and describe seismic activity, many techniques have been used and most of them focus on the phenomenon of seismic quiescence. Visual inspection of the epicenter distribution, the time-distance plots and some statistical methods as well are widely used by researchers, example Ishida and Kanamori 1977, Kanamori 1981, Taylor et al. 1991, Takanami et al. 1996. The standard normal deviate z-test is one of these statistical methods frequently used for analyzing seismic quiescence. We applied the ZMAP method for imaging the areas exhibiting a seismic quiescence. In order to rank the significance of quiescence, we used z-test, generating the log-term average, LTA, T, function for the statistical evaluation of the confidence level in units of standard deviations, Formula 3. Where RAL is the mean rate in the overall period including TW, from T0 to TE, RWL is the mean rate in the considered time window, from T to T and TW, all and sigma WL are the standard deviations in these periods, and null and NWL the number of samples, T is the current time, T0 TE. The z-value, calculated by the equation for all times t between T0 and TE to TW, is statistically appropriate for estimating seismicity rate change in a time window TW, also indicated as IL, in contrast with background seismicity. Data. The present study analyzes a catalog of earthquakes for the period 1964, May 18, 2020, University of Athens. The catalog covers data in a spatial window 33.0 to 44.0 north and 15.0 to 30.0 east with a total number of earthquakes 295,029, with depths 0 less than or equal to h less than or equal to 70 kilometers and with a magnitude ml. The catalog is declustered using the ZMAP program. The minimum magnitude of complete recording, MC, is an important parameter for many studies related to seismicity, example Taylor et al. 1991. It is well known that it changes with time in most catalogs, usually decreasing, because the number of seismographs increases and the methods of analysis improve. In seismicity studies, it is frequently necessary to use the maximum number of events available for high-quality results. In order to investigate the seismic quiescence and the frequency-magnitude relationship, the change of MC as a function of time is determined using a moving window approach with maximum curvature method, MAXC, in Woessner and Weimer, 2005. Also, MC is calculated with entire magnitude range method, EMR, as stated in Woessner and Weimer, 2005. Since the result is not changed, we used MAXC method. One can find many details on the methods, in order to estimate the magnitude of completeness of earthquake catalogs, in Woessner and Weimer 2005, Schorlemmer and Woessner 2008. The minimum magnitude of complete recording was rated on MC greater than or equal to 3.5, after which the catalog is considered complete. The events below this magnitude threshold are removed, after which 24,750 earthquakes remain. it is presented the spatial distribution of B value, declustered catalog with M greater than or equal to 3.5, for the southern part of the Balkan Peninsula, for the period from January 1, 2005 to January 1, 2011 in the figure. The spatial variations in B value change between 1 and 1.8. The highest B values, greater than 1.7, are located between 33 to 36 north and 22 to 26 east. The lowest B values, 1, are found in a large area in the SW part between 33 degrees, 38 degrees N, 17 degrees, 23 degrees east and in the SE part, where the epicentre of the studied earthquake falls, between 33 degree 37 degree N, 26 degrees minus 30 degrees E. The low value of B, B 1.0, and in the SE part in the studied seismogenic region may be associated with an increase in stress before the studied earthquake from January 4, 2011. To establish statistically significant decrease of the seismicity rate that occurs in a restricted segment of a seismogenic zone, a polygon representing is selected spatial circle with a radius of 100 km and the center of the epicenter of the studied event, 26.56 degrees east, 35.64 degrees north, presented in the figure, containing 702 events with MC4. Results obtained for the earthquake from January 4, 2011. With coordinates 26.56 degrees east, 35.64 degrees north, magnitude equals 6.2, depth equals 63 kilometers and T0 equals 13. 29, 10.5 hours of GTM. Figure shows the graph of the time change of the B value in the studied spatial window with method max curvature, sample window size equals 500, minimum of events equals 50, window overlap equals 4%, bootstraps equals 200, SMO plot equals 5. The graph of the value of B shows a maximum, B equals 1.95, around 1998, which suggests increased heterogeneity and reduced voltages, Gorgunzang, Bonhoff, Milkreet and Dresden, 2009. Since 2000 the B value decreases continuously and in 2003 reaches a minimum of B equals 1.35. The studied earthquake occurs in a period of decreasing value of B. A significant decrease in the value of B may be associated with an increasing effective level of stress before major earthquakes. Schorlemmer, Weimer, Weiss, 2004, Wu, Chang, Zhao, Teng and Nakamura, 2008. Spatial distribution of the B parameter and A value. The spatial fluctuations of B for the studied landfill were estimated for the period from 1964 to 30.03.2011. Hours before the earthquake on January 4, 2011 in the figure in ascending order are marked by low to high values of the B parameter. Spatial differences in the value of B illustrate variability in plan, and relatively low values can determine the places where an earthquake would most likely occur. Schorlemmer, Neri, Weimer, Mostacho, 2003, Westerhouse, Weiss, Yilmaz, Zhao, 2002. The zones with relatively low values of B, 0.9 to 1.2, are clearly delineated and the epicenter of the earthquake falls into them. According to Schorlemmer, Weimer, Weiss, 2004, and Motegi, Hesami, Totter, 2010. Low values of B indicate that fault stresses accumulate in these zones until the main event is activated. Note that the least squares method gives better results. The spatial distribution of the A parameter characterizing the seismic activity before the earthquake showed, estimated for the period from 2000 to 28.02.2011, that the epicenter falls in an area with relatively low seismic activity, A equals 7-7,5, but which is close to the zone with relatively high activity, west of the epicenter, A equals 8 to 9. Z statistics for the studied area. The spatial distribution of the Z parameter before the earthquake of January 4, 2011 is calculated for the same landfill, R equals 100 km, comparing two time periods, first period from 30.03.1997 to 30.03.2005 and second period from 30.03.2005 until 30.03.2011. The high, positive, Z values of the maps can be interpreted as a decrease in the flow rate of seismic events, seismic lull, compared to the first period, and the low, negative, Z values represent an increase in velocity. And in the figure, the epicenter falls in an area with relatively high values of the Z value, 4 to 5, which means that the selected period, 30.03.2005 to 30.03.2011, before the earthquake is a period of relative seismic lull. The relatively high values of Z equals 4 to 5 show 99% reliability of the result. To check result, the Z value was calculated in a circle with radius R equals 200 km for first period from 01.012005 to January 1, 2008 and second period from January 1, 2008 to January 1, 2011. In this case, the epicenter falls exactly in the zone of relative seismic lull, figure A. Figure B shows the percentage change Z in the area around the epicenter of the event is -51 to -52%, which clearly shows that around the epicenter of the earthquake during the second period a zone of relative seismic calm is formed. As this percentage change is greater than 30%, there is a significant reduction in the number of events, which makes it statistically significant. This can also be seen when comparing the spatial distribution of the number of seismic events for the first, figure C, and second, figure E, period. For the first period, January 1, 2005 to January 1, 2008, the epicenter is in an area with 100 to 102 earthquakes, and in the second period, January 1, 2008 to January 1, 2011, the epicenter is in an area with 48 to 50 earthquakes. Conclusion. The temporary change in the B value for the period 1964 to 2020 shows a minimum in the value of B equals 1.35, preceding the earthquake of April 1, 2011, ML equals 6.2, by about 7 years. Large decreases in the value of B possibly associated with increasing effective levels of stress before major earthquakes. These significant decreases in the value of B can lead to an increase in effective stress before major events. An increase in the B value after these earthquakes may mean an increase in the heterogeneity of the Earth's crust and a decrease in shear stress. The change in the spatial distribution of the B value before the earthquake shows that the area with an abnormally low value of B covers the epicenter of the studied earthquake. These low values of B can be interpreted as a potentially locked or high-stress zone before major earthquakes. Acknowledgements. This work has been carried out in the framework of the National Science Program Environmental Protection and Reduction of Risks of Adverse Events and Natural Disasters, approved by the resolution of the Council of Ministers No. 577/17.08.2018 and supported by the Ministry of Education and Science, MES, of Bulgaria, Agreement No. 01322/18.12.2019. Thank you for your attention.
Okay, thank you, Emo. The next presenter is going to be Petya Trifonova. Her topic is parameters on the seismic risk for Blagoevgrad region in Bulgaria.
Thank you, Drago. Can you hear me?
Yes, I can hear you.
Yeah. Hopefully everybody can hear me. Okay, I will share my presentation. Is it okay? Probably yes. Okay. Okay. Dear colleagues, dear guests, now I'm going to present our research, which is dedicated to evaluation of one very important parameter connected with the assessment of seismic risk. This parameter is called population exposure, and as you will see in my presentation, it refers to the people in certain area that would be potentially affected by a possible earthquake. Let's have a look at the content of my presentation. First, I will explain you why we have chosen the Blagoevgrad region. Then I will give some more information about which parameters we analyze. I will explain what data are used for the calculations and what method we have chosen. And of course, at the end, I will give you the results. Now, Blagoevgrad region occupies the so-called Kresna seismogenic zone. As you can see on the map, there is high seismic activity, which is associated with a very complicated fault system here. Two of the strongest earthquakes in Europe in 20th century were generated in the Kresna area. These are the earthquakes of April 4th, 94, with magnitude 7.1, and 20 minutes later, the stronger one with magnitude 7.8. The second earthquake was felt as far as Budapest. Many settlements were severely affected by these earthquakes. Traces of the earthquakes can be seen even now in the Kresna Valley. They activated the fault line with a subparallel direction. Presently, in the Kresna zone are registered more than half of the seismic events which occurred annually on the territory of Bulgaria. Now, some words about the population exposure and what it means. Probably most of you have seen different definitions about the term risk. Here, the term risk refers to the expected losses from a particular hazard. In our case, this is earthquakes, to a specified element at risk. The specified element at risk might be population, might be buildings, or even environment. Here, we are interested in the risk connected with potential human losses or casualties resulting from seismic hazard. One of the main parameters needed for calculating the casualties for a particular scenario is the population exposure. As I said in the beginning, it refers to the humans living in the hazard zones or the population present within the hazard area that would be potentially directly affected by an event. Now, what are the data which we have used for our calculations? We have two main data sets. First one is the seismic hazard for the territory of Bulgaria, published by Solakov et al. Last year. And the second one is 1 square kilometer grid of the Bulgarian population, which is published by the National Statistics after the last census performed almost 10 years ago. Here is presented a map of the last seismic hazard assessment of Bulgaria, performed recently by Solakov and Simonova and their colleagues. For those who are not familiar with the definition of the seismic hazard, this term is very complicated. The definition starts with probability of exceedance of some levels. I can't reproduce it exactly, but in general, seismic hazard means evaluation of the intensity of ground shaking at a given location. In our research, seismic hazard is recalculated for the influence of the ground conditions using the Global West 30 model. This exercise adds some more information about the strength of the upper crust layers. In the map, it is clearly seen from the red-orange color here that Blagoevgrad region is characterized with the highest values of peak ground acceleration calculated for 475 years return period. The calculated PGA values exceed 0.2 G and in some places 0.3 G. The second dataset which we use is 1 square kilometer population grid of Bulgaria from the census in 2011. Using the population grid rather than total number of population allows us to make a comparison between big cities and small villages because less populated towns have the same weight as more populated ones. It is similar to use the population density, but the density has one main disadvantage in the case when the settlement occupy a large area, which artificially reduce the value of the calculated density. The combination of both seismic hazard and population density provides the population exposure as an element of risk. Similar to the risk calculation, we follow the multiplicative formula that could be simplified, as you can see. We calculate the population exposure in a grid with single element 1 by 1 kilometer. Population exposure is obtained by multiplication of the seismic hazard class and population density class. Now I will show you what are these classes. To obtain the classes, we use two classification schemes. You can see them in the tables. Each variable is classified in 5 levels using equal interval classification. On the left table is given the classification scheme for the population. We have 5 classes. The largest one is above 10,000 inhabitants. Now I will show you what are the levels which we have obtained for the Blagoevgrad region. For the seismic hazard, we have classes of the upper range of the table we have values 4 and 5, and this is expected because it is due to the high seismicity of this zone. Classification of the population is in the opposite. Almost 140,000 people live in 14 towns and 265 villages. Obtained dominant levels are 2 and 3, which means that we have lots of villages with less than 100 people and some larger settlements between 100 and 1,000 people. And here I will show you the results. We calculated the population exposure. It is presented here as an index varying from 1 to 5. 1 means minor exposure, 5 means major exposure. The obtained indices for Blagoevgrad are moderate, high, and major. 30% of the settlements are characterized with moderate exposure. These are mainly small villages with less than 100 inhabitants. Major values of the population exposure are obtained for 10 settlements only. These are the places where many people are exposed to increased seismic hazard. You can see them in the list. They are mainly towns which gather 33% of the population in the Blagoevgrad region. And now some words in conclusion. We tried to obtain a qualitative information about the size of negative consequences which may occur in case of a strong earthquake. What our results show is that 33% of the population living in 8 towns and 2 villages are largely exposed to seismic hazard. If our results are combined with the specific vulnerability of the exposed elements to seismic hazard, which are buildings, for example, the seismic risk can be estimated. I would like to acknowledge the Project National Geoinformation Center, which supported our work, and thank you for the attention.
Okay, thank you, Petya. Are there any questions? Okay, there aren't any other questions. Thank you again, and we can continue with the next presentation. The next presenter is Preslav Peev, and his topic is geoarchaeological research in the area of Cape Shabwa using unmanned aerial vehicles, North Bulgarian Black Sea coast. Are you here, Preslav?
Yes, hello, everybody.
Okay. Hello, we can hear you perfectly, so when
okay, thank you.
Take it away.
Okay, thank you very much. Okay. Good afternoon, dear colleagues. My name is Preslav Peev. I'm working at the Institute of Oceanology at the Bulgarian Academy of Sciences, as well the other author, the PhD Bogdan Prodanov, who also work at our institute. The topic of our presentation is geoarchaeological research in the area of the Cape Shabwa using unmanned aerial vehicle. First of all, I'll start with the short intro to this. Just a moment. Okay. Our presentations aims to set out the role of using aerial remote sensing and marine hazard can play in informing responses to global challenges of coastal cultural heritage and enhancing the sustainable development of coastal zones. Aerial remote sensing and photogrammetric approaches are a part of modern archaeological research. In the last 2 decades of the century, a significant change in approach to archaeological research has taken place. from direct field work and excavation to remote sensing. During the last few years, our Institute of Oceanology at the Academy of Sciences conducted such types of investigations, and a lot of new data have been collected. For this initial survey has been chosen a heritage site on the Bulgarian seashore. The studied area is the archaeological site Karon Karia is the same site, just different names during the historical periods, at the Cape Shabla, and it's determined as highly hazardous of coastal erosion. The investigated area includes the easternmost part of Republic of Bulgaria. The erosion shores are common in the northern extremity between Cape Sivriburun, between Bulgarian and Romanian boundary, and Cape Shabla, being represented by Sarmatian limestone in the base, being represented by loess deposits. At Cape Shabla, the cliff shore has a generally eastern exposure, and that is why the withdrawal rate is increased approximately 30 centimeters per year. The archaeological site is located at the Cape Shabla, built on the coastal cliff. Since ancient times, the coastal area of Cape Shabla is settled by humans from prehistory, and it is very, very rich of archaeological sites and artifacts. In the area of Cape Shabla are known few sites which are very important for both geography, geomorphology, and archaeology. The first one is the submerged prehistoric necropolis situated at the reef of Lake Shablinska Tuzla, and the ancient fortress Karon Limen, our study area. The area is rich of heritage sites, but those of them which are situated on the shore are exposed to natural hazards. You can see on the left and on the right photos some of the images of the ancient fortress. The objective is to streamline the process of creating elevation data, and contours lines orthomosaic for survey detection, documentation, and monitoring of coastal archaeological sites. The remains of the sites are today visible on the cliff, but also in underwater. The most significant architectural remains come from the time of late antiquity, and especially 5th and 6th century AD, and the very early of the 7th century. The port at the Cape Shabla is mentioned by numerous of antique writers as Pomponius Mela, Flavius Arianus, who is repeated later by Anonymus Periplus Ponto Euxinium, as a port of Carians situated between Calates, it's modern Mangalia in Romania, and Chirizis, it's an ancient town situated at Cape Caliacra. The first sources mentioned that the site under the toponym Caron Limen or Portus Caria. According to Anonymus Periplus Ponto Euxini, there is a change of the name from Caria to Carea. The note refers to the locals, and it should think that there is a change in the name of the settlement as Caria pressed into Carea. Okay. The first regular excavation in this area of this ancient port took place during the second half of the 70s of the last century. Also, underwater surveys were carried out here in the 60s, 70s, and the very end of the 70s and the beginning of the 80s of the last century, directed by Mihail Lazarov from Varna and Bulgarian-Polish underwater archaeological exploration. The oldest archaeological materials get back to the late Bronze Age, is the second half of the second millennium BC. To the north of the reef at Cape Shabla, 5 stone anchors with holes were found at depth between 1.5 up to 3.5 meters. The oldest amphora have an origin of Chios Island in the Aegean and dated to the second and third quarters of the 5th century BC. Of course, as I saw earlier, the most widespread pottery found in the settlements go back to the 5th and 6th century AD. In this slide, you can see our methodology and data acquisition of collecting of our data. First step is planning of surveys, of course. The second one is cleaning of archaeological sites. It's very important because the site was covered by wastes, not only from the plants, bushes, and so on, but also from human and building works. And it's typical for all of archaeology sites which we visited during our coastal investigations. The third stage is preliminary on-site activities. You will see on the next slide what is this. The next stage 4 is flight plan and image collection with a quadrocopter, and the 5th stage is structure from motion to data processing. Yes. And this slide is the location of our unmanned aerial vehicle imagery. The red points flight altitude is 50 meters, and the yellow points have a manual mode. In this area, we covered all of the on-land part of the Caron Limen or Caria. In the underwater slope, we use different methods, and which are not will be presented at the moment. On the next slide, you see on the left photos, this is the digital surface model of 10 centimeters of resolution. On our right, very high resolution orthomosaic 0.5 millimeters per pixel. The preserved part of the area of Caria include northern city wall, this one of the tower, and a small quarter of the southern part of the site, which I show at this one. This is the southern part of the archaeological site where preserved water. Okay. Various hydrological and geomorphological changes have been modified the configuration of the coastline and paleogeographic conditions in the antique landscape significantly. The changes become more noticeable after 3rd, 4th century, when the rate of the Black Sea level rising is the so-called Nymphaean transgression increased, and as a result, the destruction of the coast. This has not gone unnoticed by the author of the Anonymous Periplus Ponto Euxini, where it's mentioned that now the land near the port is flooded. It's very important. The date of historical sources compilation is very important due to it may be the first known information about the sinking of the ancient port. Karl Müller, in the middle of the 19th century, evidenced that the 5th century, and this opinion is accepted by most scientists. All of this does not allow us to restore the exact plan and view of the settlement during the different historical periods and the colossal change in the configuration of the coast. In the present day, the coastline is different from the antiquity and medieval age. A significant part of Port City has been destroyed as a result of the Black Sea level rising and the increasing of the coastal erosion and possible seismic activities in the region. At the beginning of the 20th century, the eastern part of the settlement had already been completely lost. It's necessary to mention that the damages of Caria have also caused by construction work, using materials from the fortress during the building of the Shabla lighthouse, for example, disturbance of the cultural layers during the construction of many of military sites, military objects in the area, and also some of oil extraction activities. The archaeological and historical heritage of the area is significant. This survey aims to develop methods of mapping and detection of coastal archaeological sites using technologies such as drones that have recently become affordable. The results of the work carried out allowed us to correct and supplement the existing data as well as to prepare the basis for creating a common geoinformation space of the Bulgarian Black Sea region in the archaeological context. The general impression is that the site is subject to stress by a variety of factors and influences: nature hazards, coastal erosion, sea level rising, earthquakes, human activities, building works, tourist stress, etc. It's necessary the careful studying, including underwater, of the preserved part of the settlement and the suggestion of emergency measures for its strengthening and conservation. What is now required are the resources on a scale to match the demands of this new and challenging agenda. Our presentation is supported by the project Inventory of Late Antique and Medieval Ports along the western Black Sea coast, which is founded by the National Scientific Fund, and it's under a grant agreement between Bulgaria and Austria. The archaeological sites were photographed through quadrocopter, acquired under the project Mapping and Monitoring of Depositional Areas along the North Bulgarian Black Sea coast using unmanned aerial vehicle, also funded by the National Science Fund. Thank you very much, colleagues.
Okay, thank you very much, Preslav. Does anybody have any questions? If there aren't any questions, we can continue with the next.
Okay, thank you, bye-bye.
Thank you.
Good luck.
Thank you again, Preslav. The next presenter is Dimchu Sulakov. His topic is earthquake scenarios for the city of Ruse. Are you ready?
Okay, do you hear me?
Yes, I can hear you.
Okay.
Okay, go ahead.
Oh, this is... Okay, do you hear?
Yes, we can see the presentation.
Okay. I will present you some results concerning the earthquake scenarios for the city of Ruse. Why Ruse? Ruse is the one of the largest cities in Bulgaria, and the city is influenced very strong from the intermediate earthquake in the Vrancea region. There are two approaches to prepare the deterministic scenario for a given site. One is to choose a reference earthquake specified by a magnitude or an epicentral intensity associated with a particular earthquake source, fault point, crustal volume, or second, directly showing values of local macroseismic intensities or of instrumentally measured parameters if they are available, generated by a damaging real earthquake of the past. In the first case, the local ground shaking levels usually need to be evaluated through attenuation relations for the selected parameters. In the second case, the most common situation is that of single or few intensity values that describes the severity of the effects on the built environment caused by historical earthquakes selected as representative. The most important feature of the approach is that the deterministic scenario must be consistent with the seismic history of the city and with known active faults close to the city. As I said, the city of Ruse is one of the largest earthquake-prone cities in Bulgaria. Ruse is the fifth largest city in Bulgaria with population of about 160,000 people. It is situated in the northwestern part of Bulgaria and on the right bank of the Danube River and Frusinski Lom River. It is the most significant Bulgarian river port. In the present study, the deterministic earthquake scenario in terms of macroseismic intensity that are consistent with the seismic history of the city are generated. The seismic hazard for the city of Ruse is controlled by the Vrancea intermediate depth source in Romania. And this source is located of about 150 kilometers to the north from the city. The scenario earthquake ground motion fields in Ruse are derived postulating strong intermediate depth earthquake in Vrancea. The methodology used consists from 7 steps. First, compilation of regional seismotectonic database. Second, analysis of regional seismotectonics. Evaluation of the seismic potential of active structures. Geotechnical characterization of the studied area. Selection and weighting of appropriate ground motion prediction questions consistent with the seismotectonic features of the region. Selection of the scenario event, and at last evaluation of the ground motion parameters. The case of Ruse is comparatively simple because there are no active faults close to the city, and hazard, as I said, the hazard is dominated by the Vrancea earthquake. So it is easy to choose the earthquake for a scenario. A few words about the Vrancea seismic zone of Romania. It is a very particular seismic source, often described as unique in the world, and it dominates the seismic hazard for most of the northern part of Bulgaria. The events generated in this seismogenic zone are characterized by relatively deep hypocenters and wide area of macroseismic impact. The depth of earthquakes is between 90 and 230 kilometers. The strongest known event in this zone is the earthquake from 1802 quake with magnitude, evaluated magnitude 7.9. The 1940 earthquake with magnitude 7.7 and well-known 1977 quake with moment magnitude 7.5. Situated at distances larger than 200 kilometers from the Vranchea zone, several cities in the northern Bulgaria suffered many damages due to the high energy Vranchea intermediate depth earthquakes. Here you can see some damages in the city of Svishtov. Soil properties in the city region. They could be recognized for blocks, and the representation of soil properties was defined by the engineering parameter VS30. This is the average airway velocity in the upper 30 meters of soil rock profile. The most widespread soil marked with block 1 is quaternary loss with thickness over 30 meters. Block 2, these are alluvial formation on the full terraces of the Danube River and Rusinski Lom River. Block 3, cohesionless sands with thickness of about 10-12 meters that are characterized by pronounced liquefaction properties. Here you can see this block, and block 4, organic and oolite limestones from the Rusi formation. This block is with the highest VS30 velocities, which reaches 550 meters per second. Crowd motions are very important part from the evaluation of scenarios for a given site. The selection process of adequate ground motion prediction equation started from a comprehensive list of available ground motion models, to which a set of exclusion criteria was applied according to similarity of the tectonic environment, variety of the underlying datasets, and so on. The following 3 attenuation relationships were selected for intermediate depth earthquakes. This is BG hydro attenuation relation by Abrahamson et al. Young's 97, Young's et al. 1997, and Vacarianu et al. 2015. It should be mentioned that Vacarianu attenuation relation is based on data from Vranchea earthquakes and from other parts of the world, while these two attenuation relation do not include data from Vranchea earthquakes. The method introduced by Scherbaum so-called log likelihood is chosen for testing the models against the observational data. This method provides a ranking criterion based on information theory. This technique is based on the probability for an observed ground motion to be realized under the hypothesis that the model is true. Here you can see the results, which are based on 1073 observations for magnitudes greater from 5.2, and here from 97 observations for stronger earthquakes with magnitude greater than 6. Because earthquakes magnitudes between 5 and 6 does not influence seriously the city of Ruse, we take the observations for magnitude greater than 6 as criteria for choosing of ground motion prediction earthquake. Deterministic earthquake scenario in terms of macroseismic intensity generated for the city of Ruse. The scenario is based on both local seismic history of the city and tectonic environment. The scenario earthquakes was chosen with moment magnitude 7.5. This is the Vrancea earthquake from 1977 with depth 94 kilometers at hypocentral distance from the city, 240 kilometers. It should be mentioned that concerning the Vrancea earthquake, Ruse can be considered as a point. The ground motions in peak ground accelerations are calculated using Vaccareanu and all attenuation relationship, and the estimated peak ground accelerations are converted into intensity applying these two relations, where PGI max is the maximum of two horizontal components and PGA GM is the geometric mean of two horizontal components in centimeters per second. Here are presented the observed and predicted ground motions from intermediate depth Vrancea earthquakes. These are the strongest earthquake after 1900, and the data presented in the table show a good agreement between observed and predicted intensities. And this shows that we can use this procedure for evaluation of the scenario for the city of Ruse. Okay, here you can see the scenario for the city of Ruse. The figure illustrates the macroseismic intensity for the 7.5 magnitude earthquake. In the deterministic scenario, the predicted intensity is assigned to block 3. Intensity for block 2 is increased with 0.5 units because of the high groundwater level near Danube River and along the Rusinski Lom River. For blocks 1 and 4, the intensities are decreased with 0.4 because the observed impact of 97.7 earthquake of block 1 this and for block 4 because of the high values of VS30. The generated scenario earthquake is consistent with the conclusion after the 1977 Vrăcea earthquake. The consequences decreases with distance from the Danube River. It should be noted that the intensities in deterministic earthquake scenario for the city of Ruse will increase with half intensity unit for magnitude 8 with depth 150 kilometers and at hypocentral distance 256 kilometers. Conclusions. A deterministic earthquake scenario in macro seismic intensity is developed for the city of Ruse. The work on scenario was guided by the perception that used and realistic ground motion map had to be produced for the area. The intensity values varies between 6.5 and 70.5. It should be emphasized that ground motion prediction earthquakes that is presented with Bacariano et al. And the conversion relation in Ardeleanu 2020 are useful tool for seismic hazard assessment and deterministic earthquake scenario generation. Estimation of deterministic earthquake scenarios for a city is one of the most important challenges in the field of seismology. Moreover, it is a key step in the evaluation of seismic risk and loss estimation for a city. The generated scenario map is reliable and can be used for developing risk scenario for engineering decisions and infrastructure planning and insurance for a given city. The earthquake scenarios are intended as a basic input for developing detailed earthquake damage scenarios for the city and can be used in earthquake safe town and infrastructure planning. Acknowledgement. The present study has been carried out in the framework of the National Science Program, Environmental Protection and Reduction of Risks of Adverse Events and Natural Disasters. Here you can see the number of the project. Thank you for
Благодаря много за Thank you very much for the presentation. If I can just ask Vasco Golubov to turn off his microphone because everyone.
Yes, sorry.
It's not a problem. Okay, so if anybody has any questions on this presentation. Okay, then, if there aren't any questions, we can continue with the next presenter. Thank you, Dimchu. The next presenter is Dimitar Stefanov. His topic is complex assessment of the urban earthquake risk. Are you here, Dimitar? I cannot hear you. Maybe unmute your... Oh.
Now?
Oh, yeah, we can hear you now.
Okay.
Go ahead.
The seismic risk analysis addressed to earthquake emergency management and protection strategies planning requires vulnerability and damage evaluation performed at territorial scale. The result provided by a seismic risk analysis could be regarded as helpful guidelines with respect to all the phases of the seismic risk management during normal periods during crisis periods as well as in the recovery and post-emergency periods. During normal periods, a seismic risk analysis can provide the support to formulate general strategies for earthquake mitigation and disaster response planning. The casualty evaluation allows judging whether medical care and emergency response essential facilities are sufficient compared to the estimated consequences. In the post-emergency period, the seismic risk analysis allows identifying the most effective solutions to rebuild, choosing interventions that may represent an improvement to the future. Methodology for seismic risk assessment. The present study is based on the methodology for analysis, evaluation, and mapping of seismic risk of Republic of Bulgaria, developed by National Institute for Geodesy and Geography for the Ministry of Regional Development and Public Works, approved by the Minister and having the force of normative document. The first step is to identify the regions with equal macroseismic intensity, referring to the seismic intensity map. Then each building is assigned to a relevant vulnerability class following a procedure based on EMS. The buildings are grouped according to their vulnerability class from A to F. To each group of buildings, the number of those that reach certain damage grade is calculated directly using the values of damage probability matrix for the vulnerability class and depending on the seismic intensity for the location of the building. The buildings with equal damage grade are selected among all the buildings in the region with equal intensity and belonging to the same vulnerability class. In that way, the number of the damaged building is determined. Subsequently, the area of the damaged buildings, according to the damage grades, is also calculated from the GIS database for the region. That area is used to assess the monetary loss and the human casualties. The approach is applied to each elementary cell of the GIS representation of the region. Usually, the dimensions are 400 by 400 meters. Case study 1, Town of Sivlievo. The town of Sivlievo is located in central North Bulgaria. The seismic risk assessment is made for 3 scenarios corresponding to 3 levels of seismic input. Seismic intensity 7, indicative base for relatively weak earthquake. Intensity 7.5 corresponds to seismic excitation with a return period of 475 years. This period is typical for the buildings codes, and especially Eurocode 8, which concern the design of the new buildings in our country. And finally, the seismic intensity 8, which corresponds to seismic excitation with a return period of 1,000 years. The population is 20,000 people, according to the data from the statistics. And in the table, you can see the distribution of affected people, injured and victims. Methodology provides 2 different ways to calculate these numbers during the day and during the night, because there is a significant difference if the earthquake is happened in the day or in the night. You can see the results in the table. In the next table, you can see the distribution of injured by category. And there are 3 categories. S1, this is minor injuries. S2, in need of hospital treatment. And S3, severely injured. This information usually is very important for the next steps in the process. In the second table, you can see the number of homeless people need for accommodation for 3 cases. These 2 tables shows the distribution of buildings, the first one by number, and the second one by total floor area in square meters, in different damage levels. as can you see, the damage levels are 5: slight, medium, heavy, very heavy, and destruction. And for every level, we calculated the number of buildings and the total floor area of these buildings. In the next table, you can see the distribution of buildings by area, but in percent in different damage levels. And the final table represents the economic losses in thousands of Bulgarian leva in the main groups of buildings. The main groups are three: residential, industrial, and administrative and special. We did this division because of the reason that during the night, all people are in the residential building. During the day, the working people go to an administrative and industrial building. The third group, special building, in this group, we include buildings which are important in the after-earthquake period. These are schools, hospitals, police stations, fire stations, and other special buildings. Case study 2, town of Bogorgrad. Bogorgrad, there is another approach. The seismic input is a little bit different. The analysis is performed for deterministic scenario in terms of microseismic intensity, but in this case, the intensity map is based on a seismic scenario in terms of peak ground acceleration and velocity on earthquake with magnitude 6.5, with rupture under the city. The territory of the city is divided into cells which size 400 to 400 meters. The intensity is calculated for each cell separately based on the data from the engineering geological studies. The mean value of the intensity of all cells is 8.65. In the next table, you can see the distribution of affected people, injured and victims during the day and the night. The next table is the distribution of the buildings in different levels of damages into variants like PFA. And finally, we can see the economic losses in the main groups of buildings. The main topic of this paper is complex assessment of the urban seismic risk. One task facing the state authority is mapping the seismic risk for the territory of Republic of Bulgaria. Seismic risk mapping can be done in different ways depending on which authority will use the information and for what purposes. The first stage of the work includes a quantitative assessment of losses, social, material, and economic. In the second stage, it is necessary to apply an approach on calculating a complex numerical risk assessment, which will allow comparison of data for different regions, cities, etc. In the present work, an approach for calculating a complex assessment of the urban seismic risk is applied. The proposed approach is based on the normative document guidelines from 2017, which is applied by all structures of General Directorate Fire Safety and Protection of the Population in Bulgaria. All disaster response plans are developed on its basis, and this makes it important for the overall seismic risk management process. For seismic risk, the potential adverse effects are determined in the following areas: social consequences for people and disruption of normal social function, the potential number of dead, seriously injured or injured, as well as the number of people directly affected, evacuated, and temporarily accommodated persons. Material consequences, damage to buildings, facilities, and finally economic losses, the total losses in Bulgarian leva for all categories, including the cost of immediate or long-term recovery measures. The overall approach is based on consequences assessment. For the purpose of the consequences are divided into 5 levels from minor to catastrophic, and each level is assessed with the corresponding number of points. In the second column, you can see the description: minor, small, moderate, severe, catastrophic, and for every level, they give some points. The social consequences can be evaluated in several directions. First direction is potential death toll. And usually the criteria for catastrophic is potential number of deaths directly caused by dangerous event, disaster, are bigger than 1 per 10,000 population in the city. You can see the severe first case, there are 6, 10, and because the population is 20,000, this number is bigger than this, so according to the criteria, the consequences are catastrophic. The same is situation with another cases. The second direction is potential number of seriously injured. Here we have again catastrophic because the criteria is almost the same, more than 1 per 10,000 population. The third possibility is potential number of people affected immediately from the earthquake. Here for the severe intensity 7, we have consequences level severe, between 100 and 1,000 evacuated, moved, and temporarily accommodated persons. We have from our calculations 310. For severe 7.5, the same, but for severe intensity 8, we have catastrophic, because the criteria is more than 1,000 people affected. For the Volgograd, against the level is catastrophic. The material consequences are determined on the basis of the distribution of damages, the percentage distribution in the unfolded build-up area. The 5 levels of consequences correspond to the damage levels. Only the catastrophic level corresponding to the levels of damage, very heavy, and destruction. Here is this table, the results. Multiplying the area by the parameter B, points at each level of consequences, gives the numerical value for each level. Assuming these values, we get the final column, which represents the results. In practice, this is a weighted assessment of impact of each individual damage level on the overall assessment of the material consequences. The assessment of economic consequences is based on comparison of the value of monetary losses with the part of gross domestic product, GDP, on the region, in our case in the city. On this table you can see that economic losses can be evaluated as catastrophic in all cases. This is the losses calculated for every case, and this is GDP for the region. And the level of potential harmful consequences for seismic risk is formed by 3 factors: social consequences, material, and economic losses, which have different relative weight. The final numerical value is obtained by multiplying the numerical values for the determined levels of consequences in the 3 areas by the respective weighting factors and summing them. Here is the weighting factors. The social consequences, there is 50% weight due to the high priority of protection of human life and security, as well as the community preparedness, response, and recovery. The material consequences, 30% weight due to the importance of the protection of the building and infrastructure. And finally, 20% for the economic. The final numerical value is obtained by multiplying the numerical values for the determined levels in the 3 areas. And this is the final results. They are different for every case. And it is possible to compare two towns or two villages or one small town with one big town and so on. And finally, the conclusions. The assessment of the consequences of earthquakes is based on procedures for integrating seismic hazard with the seismic vulnerability of building structures. A detailed quantitative assessment of the consequences in the form of losses includes assessment of direct damages and destruction of the building stock. This fact is important and should be taken into account when planning the necessary resources, building materials and labor to recover the damaged building stock. Assessment of social losses, injured people and victims. The assessment of casualties and injuries is based on parameters that take into account the specific conditions in the study area, such as type of construction, system, building density, time of event, etc. The number of people who remain without shelter, need for accommodation is determined. Estimation of economic losses due to direct physical damage and destruction of the building stock. These amounts can be used to develop disaster response plans and plan the need for financial resources to rebuild the buildings. Based on the results of the detailed seismic risk assessment for two Bulgarian cities, an approach for complex risk assessment is proposed, which will allow direct comparison of the numerical values for different cities, municipalities, or districts. The approach can be applied in practice in the forthcoming seismic risk mapping for the Republic of Bulgaria. Thank you for your attention.
Thank you very much, Dimitar. Does anybody have any questions? If there aren't any questions, first of all, thank you again, Dimitar. And we can continue with the next presenter, the last of this session, Plamen Ivanov, whose topic is Assessment of Landslide Susceptibility and Hazard along the northern Bulgarian Black Sea coast.
Good afternoon. My name is Plamen Ivanov. I'm from Geological Institute of Bulgarian Academy of Sciences. You can see my presentation, Assessment of Landslide Susceptibility and Hazard along the northern Bulgarian Black Sea coast. The aim of this publication, the aim of this study is to identify area prone to landslide along the northern Bulgarian Black Sea coast. For this purpose, the method of Mora and Varson was used, which was applied in compiling the map of landslide susceptibility for the region. This method was already being successfully applied in Bulgaria for the region of the Sofia Valley, as well for the Bulgarian Black Sea coast. This publication attempts to apply the method to a part of this area where there is a concentration of landslides. The geological structure and the special lithological varieties in this area have an impact on the landslide susceptibility along the coast. Much of the northern Bulgarian Black Sea coast is covered by old, conditionally stabilized or active landslides. This originated in Sarmatian sediments composed of limestones, diatomaceous clays, aragonite clays, and sandstones due to fluctuation in sea level during the Pleistocene and seismic impacts. In the region along the Varna and the Baltic coasts, there are two types of landslides: circus for the Varna landslides region and linear stepped package for the Baltic landslide region and the landslide region Kamenbryak. Of these old landslides in the area of the resort near Varna, only the coastal part is usually active under the action of sea abrasion, in contrast to Baltic, where a large part of the landslide slope is unstable. Here you can see the distribution of landslides on the northern Bulgarian Black Sea coast. conditions and factors for the occurrence of landslides process. The northern platform part of the Bulgarian Black Sea coast is built of almost horizontally laying sedimentary rocks of tertiary and quaternary age. The terrain in the coastal part of the Varna depression has a plateau-like character. In the section north of Varna, there are two plateaux, Frangea and Dobruja, separated by the valley of the Batuva River. The altitude at the edge of the plateau decreases in a northerly direction. The main factors influencing landslide activity are the slow vertical movements of the Earth's crust, earthquakes, abrasion, impact of surface and groundwater, and man-made activity. Assessment of landslide susceptibility along the northern Bulgarian Black Sea coast using the Mora and Varsom method. In the present study, the Mora and Varsom method is applied to assess the landslide susceptibility along the northern Black Sea coast, which is affected by landslides. The method is based on the weight assessment of various adverse conditions and destabilizing factors on slope stability. A modified method proposed for the region of the Bulgarian Black Sea coast with an additional triggering factor, abrasion, erosion, was used to assess the susceptibility to landslides. The landslide hazard is expressed by the following equation using a GIS. You can see a formula where susceptibility factors are slope factors, lithology factor, soil moisture factor, and triggering factors are seismic intensity factor, precipitation intensity factor, erosion abrasion factor. The description of the factors involved in the assessment of susceptibility is taken from table with set points proposed by the authors of the method, Mora and Varson. The slope factor takes into account the maximum difference of elevation of the terrain per unit area, natural rugosity. Then was used for the zoning of this factor. The lithology factor is determined depending on engineering geological properties of the lithological varieties that makes up the study area. In the original approach proposed by Mora and Varson, this indicator varies from 1 to 5, with 1 point given for the strongest varieties and 5 points for the weakest. In the present study, an adaptation of the method was made according to the engineering geological conditions typical for the northern Bulgarian Black Sea coast, in Table 1. 4 categories are selected, which are shown in Table 1 and in Figure 2. The weakest and respectively most susceptible to landslide process are the youngest lithological varieties with neogene and quaternary age, mainly clay and cohesionless soils. Of particular importance for the development of landslides are unlithified, unconsolidated aragonite sediments of the Tupola Formation, distributed from the village of Kranevo to the town of Kavarna. Here you can see lithologic factor criteria, characteristic for the northern Bulgarian Black Sea coast, with 2 points. This is rock formation, sedimentary rocks, neogene, paleogene age. This is limestones of Odrci formation. With 3 points, this is porous limestone, Carbona formation. With 4 points, alternating sedimentary rock, paleogene, and weathered rock. This is the Ruslar formation, Avren formation sediments. 5 points we give of diluvial and alluvial deposits, clay sediments of Quaternary, Neogen, and Paleogene age. This is sands, gravels, clays, marine terraces, sediments, clay loess, unlithified unconsolidated aragonite sediments of Tupola Formation, also sands of Range Formation, clays of Euxinograd Formation, sands and clays of Galata Formation. The soil moisture factor is determined in accordance with the accumulated value of the precipitation index, varying from 1 to 5. For the country, however, its maximum value is about, and for the coast, it is below 1.5. In the present study, the soil moisture factor was determined on the basis of data published by Koleva and Peneva. The data needed to determine the precipitation triggering factor were taken from the same source, Koleva and Peneva. According to the seismic zoning of the country, which is referred for 1,000 period, the seismic intensity factor for the northern Bulgarian Black Sea coast vary from 5, this is 7 degree according to MSK 64, to 7, this is 9 degree according to MSK 64. And in the seismically active region near Shabla, Kaliakra, it has a value of 7. For the zoning by erosion abrasion hazard, the map of the geological hazard in Bulgaria was used, and for the coast, data from Shwisky and Simeonova, and from the project elaboration of analysis, evaluation, and mapping of geological risk. The following results for the erosion and abrasion factor are presented in figure 3. Here you can see susceptibility factors of the northern Bulgarian Black Sea coast. First figure, this is slope factor, second lithology factor, and soil moisture factor. Triggering factors of the northern Bulgarian Black Sea coast. This is seismic intensity factor, precipitation intensity, and erosion abrasion factor. Map of landslide susceptibility and hazard. Landslide susceptibility is calculated according to Formula 1 and is shown in figure 4 using a classification scheme in 5 classes. The results show the terrains where we can most likely expect manifestation of landslides. The location of the landslides in the area is also shown. In table 2, you can see classification of landslide susceptibility in 5 classes. Here the result map, landslide susceptibility and hazard along the northern Bulgarian Black Sea coast. In the second map, you can see the manifested landslide with this purple contour, purple line. Conclusion, the analysis of the factors influencing the stability of the coastal shows that they have a higher concentration in more intensive impact on the northern part of the Bulgarian Black Sea coast, where most of the larger landslides occur. Particular attention is paid to the special lithological varieties in this area, influencing the landslide susceptibility. The compiling landslide distribution maps are the first step to subsequent assessments and landslide hazard and risk maps. As can be seen from the result expressed on the susceptibility map, the maximum number of points obtained in the assessment of the northern Bulgarian Black Sea coast is 345. This corresponds to a medium degree of hazard according to the original methodology of Moore and Varsun. The slopes along the Varna and Balchik coast are most susceptible to landslides with 226 points. Deep landslides with periodic activation of parts of them prevail. The majority of the study area is characterized by moderate and low degree of landslide hazard. Acknowledgement: this work has been carried out in the framework of the National Science Program, Environmental Protection and Reduction of Risk of Adverse Events and Natural Disaster, supported by the Ministry of Education and Science of Bulgaria. Okay, thank you for your attention.
Thank you very much, Płamen. And now, as this was the last presentation of this session, are there any questions on all the presentations from this session, including this one? If there aren't any, thank you again. And now there's going to be a short break until 3:30, after which we're going to continue with natural hazards and risks.
announce the first speaker. Her name is Petya Evtimova.
Hello.
Hello. Nice to meet you here. She will tell us about her research connected with assessment of empirical relationships between beach face slope and sediment size using field data. Welcome. We are going to hear your presentation.
Thank you very much. I'm trying to share my presentation. Yeah. All right. So I'll speak about a small an initial assessment of empirical relationships. I'm sorry, just excuse me. Excuse me for interruption. All right. So the study name is Assessment of Empirical Relationships between Beach Face Slopes and Sediment Sizes using field data. We are talking about Burgas Bay case. Me and my colleagues work in the Institute of Oceanology from Bulgarian Academy of Science that's located in Varna. This study is a small part from a bigger study from the executed in the National Science Program, Environmental Protection. I'm not sure if you hear me. Is it okay?
Yes, we hear you very well and
okay.
can see everything.
Oh, all right. Great. Sorry for interruption. So the program name is Environmental Protection and Reduction of Risks of Adverse Events and Natural Disasters. And our task is called Assessment and Risk Reduction Measures to Unfavorable and Extreme Hydrometeorological Events on the Coastal Environment. During this program, we took many sediment data from the coastline of Burgas municipality and Pomoria municipality, and also we covered making digital surface models from many parts of this coastline. And we decided to test the available relationships between the beach face slopes and sediment sizes for several stretches located in Burgas Bay, and but this was a limited field data, and still it explores these relationships, explores the applicability of a number of previously developed formulations for local geomorphic, lithologic, and wave conditions. The knowledge on the clear dependence between considered parameters is of particular importance for many engineering applications. That is, calculation of maximum run-up, shoreline changes, beach berm erosion potential, and assessment of local flood and erosion hazards. These are, here you can see our study sites. Located in Burgas Bay, as I said. This is Pomoria Sandspit, Kraimoria, and Chingeneskele. Pomoria Sandspit is located along the northern arm of Burgas Bay and encompasses the second longest sandy beach along the Bulgarian coast. The coastal area has eastern exposure. Kraimoria coastal area is located to the south of Burgas city and encompasses 3 natural sandy beaches baked by relatively low cliffs with northeastern exposure. And Chingeneskele, the third one, is situated further east from Kraimoria and is heavily man-modified small bay with northwestern exposure. So what about the data? So we needed sediments, data about for the sediment characteristics. Sediment data were gathered simultaneously with the terrain data using two field surveys. The sediment samples were taken at the shoreline. This is the lower part of the beach face from the upper 5th surface layer. For the three sites, it could be said that sediments vary from fine to coarse sands according to Wentworth size scale. You can see the photos of the sediment samples used and photos of the three study sites. And now about the topography data. WAF-based surveying of the Bulgarian Black Sea coastal zone took place, and we used the products of this surveying in terms of digital surface models, and we took 18 profiles along the three sites and calculated the beach face slopes through using the parameter tangents beta. What about the wave data? With respect to wave climate, values of significant wave height, means and maxima of wave entering Burgas Bay are calculated to be about 0.6 meters and 6 meters respectively. Propagating toward the coast, they are being transformed, and near shore values range within 0.3, 0.5 meters for mean values, and 2.5 to 5 meters for the maxima. About the peak wave period, it is uniform through the bay, 4 to 5 seconds for means and 10 to 11 seconds for maxima. At the left, you can see different stages from making the digital surface model. And this is Pomorius and this bit. And so we have the data, and we had to test it with different available formulations. I have to say that there are many of them following different approaches. So the first one is are those of Tsunamura for prediction of the beach slope phase based on breaking wave height, acceleration due to gravity, median grain size, and wave period using data from 3 field locations and 12 laboratory studies. The one Uda and Sakai, their relationship is between beach face slope, sediment size, and significant wave height. That of Race and Gamma connects sand sites, offshore wave height, and beach face slope using data for 2 spots on the southwestern Portuguese coast. Fleming suggested relationships between 2 main parameters for different beach states. He suggested using the surf scaling parameter of Guza and Inman or the Dean parameter to differentiate between morphodynamic states of the profile. According to the surf scaling parameter, the beach states are determined as reflective and intermediate, and you could see the 2 equations suggested by Fleming. The beach face slope equation in Kim is based on analysis of laboratory data sets defined by the D50 and tangents beta, and they use also the wave period. Buyan et al. Conducted a large-scale study on very wide range of sediment sizes and beach face slopes. They analyzed the very big amount of field measurements. They used 2,144 field measurements from 78 studies of different scale, and they try to make it universal, but okay, you will see later. Covering grain populations with median sizes from 0.063 millimeters, which is very fine sand, to two boulders. And McFall, the last equations, a group of equations, developed three relationships: independence of wave exposure for protected, moderately protected, and exposed beaches, based on grain size and beach face slope, for using data from 181 locations. And the results. So at the left, you could see the behavior of available feed data pairs of tangents beta and D50. It can be seen that the tangents beta increases with increases of D50, which confirms the many previously identified trends in literature. The regression analysis of data reveals that the polynomial fit provides the best approximation. On the right side, you could see, you could see a representation of field data against all selected predicting formulations, just in order to see where the data goes with all formulations. But the formulations are applied for from 0.1 millimeters to 1 millimeter. I mean continuous values with a step of 0.1 millimeter. It is observed that the measured data pairs fit relatively well in prediction area prescribed according to McFall, Boyan, Fleming, Uda, Kim, and showing similar behavior of tangents beta with the increase of D50. But the expressions of Rice, Gamma, Sunamura deviate significantly, illustrating the opposite dependence. So on the next page, on the next slide, so we decided to make an analysis, because all formula follow different coastal types, or they're prepared for different morphodynamic state, or some of them are accounting only D50 and possibly influenced by wave parameters. So in figure A, you could see the formulations of McFall and the in situ data for exposed and moderately exposed beach profiles. I'm sorry. In B, you could see the formula of Boyan, Uda, Kim. That oh, I'm sorry, I switched so I'm sorry. At B, you could see the Fleming's formula for dissipative and intermediate beach state, and the in situ data. And the third one, the figure C, you could see the fits for Boyan, Uda, and Kim's formulations, and together with the in situ data. They account only for D50.
Трябва да Евтимова нещо презентира. Аз трябва да ето ме. Аз се виждам къде съм, дали ще успея да си оправя, ако не, дали ще успея да си кача.
Само ще ви помоля да си изключите микрофона и тогава да се качвате. Петя.
Да, благодаря.
You can finish.
Да. Oh, sorry. I'm sorry, I switched to Bulgarian. So you could see that with respect to the second group of relationships, they predict beach face slopes in very narrow ranges. I am talking about figure C, expressing the similar behavior, but Kim et al. Calculates steeper slopes compared to the other two formula. And several conclusions could be made. So I have to say again that the main goal was initial assessment to explore the applicability of these 6 formulations to local geomorphic, lithologic, and wave conditions. Several formulations can be considered gene for future exploration. That's the Fleming's equations, McFall's, and partially Uda, Kim, and Buyan. So the main drawback is lack of sufficient field data pairs. Yeah, we need more data pairs just to be sure in our conclusions. And the specifics of the local sediments, I have to say that there is a presence of magnetite fraction at almost all of the beach profiles, which alters their dynamic properties. And another one that is not included in the slide is that the wave conditions used to create all these empirical formula are mostly from oceanic conditions. So yeah, it's normal just that we could expect different behavior of these formulations at the local scale. And if we have more data, we could produce suitable formulations and just to adjust the coefficients to cover our local specifics. And I have to stress to the importance of regular coastal monitoring. That's yeah, it could be said for many scientific fields. And the expected future development is elaboration of native relationships accounting for the local to regional specifics of the Western Black Sea coast, and expanding the database to cover wider range of beach face slopes and sediment sizes coming from areas with different wave exposure and morphodynamic state. And this is coming in the future, I guess. And I have to say that thank you for your kind attention. I'm sorry if I interrupted it too much, but yeah, that's it. Thank you.
Thank you, Petya. It was perfect. Dear colleagues, yes, if you have questions, please write them in the chat. Now we are moving from Burgas area to Sofia Kettle. We'll hear a presentation from Miroslav Krastanov, which is about the assessment of destabilizing factors on a potential landslide slope in Sofia Kettle. Example from the village of German. So, Petya, mute your microphone.
Oh, yeah.
And welcome, Miroslav. The floor
Hello,
is yours.
everybody.
Hi.
Do you hear me?
Yes.
1 second. I try to share. One second.
Yes, we can see.
Okay.
Now.
Good afternoon, everybody. My name is Miroslav Krastanov from Geological Institute, Bulgaria Academy of Science. I'm glad to present my article on the topic assessment of destabilization factor contention landslide and slope in Sofia Kettle. Example from German village area, Bulgaria. The Sofia Kettle has been selected as one of the regions in the country where landslides often occur due to anthropogenic impact. The concussions are often associated with significant material damage, cracking and destruction of buildings and facilities, disruption of transport infrastructure, and sometimes human casualties. And this slide I show panoramic view of investigation slope on the village German. The favorable condition of occurrence and landslide with anthropogenic characteristics are the cutting of steep slope, the diverse geological structure, and the low value of the shear strength of the geological variation. The stability of the slopes in most destabilization by heavy embankment, low slope filling, the weathering of clay deposit, dynamic impact from vehicle, the correct choice of physical and mechanical properties of earth-based material, the forest-started slope, and earthquake. The considered terrain to which slope research 49 degrees is also flotation and damage and endangered by landslide. The study terrain is located southeast part of village of German. Geomorphological for region is north periphery of the Peruvian deposit of the foot Lozensk mountain. The study terrain is flat is 63% of its area, and its other part is steep with slope from southeast to northwest. Average altitude, the flat part of the property is 519 to 591 meter, and its steepest part is 598 to 599 meter. The height of slope research is 10 meter. The terrain morphology is additional modeling by anthropological impact. In the case is embankments. And this slide I show a topographic map of terrain with location, engineering, geological cross-section. Here I show you cross-section 1, 2, 3, 4, 5, 6. Here is highest part of investigation terrain. And the slope, I show you how is look cross-section 1, 2, 3, 4, 5, 6. The first layer is present as embankment material, and second layer is present clay to sandy clay, and the basic of the cross section is present by block boundary conglomerate, quartz sandstone, and andesite. The layer 1 is embankment. It is a systematical length and represent from powdery clays to powdery sandy clay with small to medium gravel, in places ridgy boulders. The stability thickness of the embankment is 2.30 to 8.70 meter. Layer 2 quaternary clay. It's represented by brown powdery clay with in medium to hard plastic consistency. Layer 2 is stability joint throughout the study area. Layer 2 lies under layer 1 at the depth of 0.30 to 8.70 meter from the ground surface. The thickness of the layer is 0.80 to 0.90 to 50.16 meter from the moderate level on the terrain. Layer 3 is block boundary rock species. Layer 3 lies under layer 2 at the depth 0.80 to 20 meter from the ground surface. The layer is represented by block boundary quartz sandstone, andesite, tuff, and conglomerates. Layer 3 is stability everywhere in the study terrain. It's a thickness over 2.50 meter. Shear strength parameter obtained by the laboratory plane shear test on undisturbed soil samples, and from heavy type penetrometer DPH penetration test. In the table 1, I show you values of physical-mechanical parameters on different strata. The layer 1 average volume from bulk density is 80.7 kilonewton per meter cubic meter. Angle of internal friction is 20.9 and cohesion is 31.0. For layer 2, bulk density is 19.3 kilonewton per cubic meter. Angle of internal friction is 40.1 degree. Cohesion is 26.0 kilonewton per square meter. Layer 3, build density is 26.0. Angle of internal is 31, and cohesion you can see is very high value, 5,960 kilonewton square meter. During the steady groundwater at the depth of up to 30 meters was not detected. The current degree of stability of the slope is determined by three representative profiles, shown in figure 2, 3, and 4. For estimate slope stability for representative cross-section, we use Wallenius method. With this method, only valid for circular from slide surface, interface forces are ignored, and thereby the unknowns are reduced to n values of normal force, n values of shear force, and safety factor. In this slide, you can see calculation cross-section 1 to 1, 2 for slope stability in natural state. Here, and yellow color is layer 1, medium layer 2, layer 3. Here is network from circle center of rotation, slope rotation. This is slide, cutting slide. Number 1, 2, 3 to 10 mark OML from landslide body. And the figure 5, I present a computation cross section 3, 4 for slope stability in natural state. And figure 6 is calculated cross section 5 from 6. When computation geomechanical model, the result of engineer geological study of geomorphological feature of the slope and the physical mechanical indicators of the construction so were taken into account. The slope analysis were performed with problem slope of the Italian company Geostru on 449 sliding surface. The following variations have been studied: stability of slope in its natural state and basic combination of loads and water saturated slope and loading slope and earthquake on 9 degrees. The result of stability analysis is shown in figure 4 and 5 and 6. You can figure 6. This figure shows the contour of sliding surface which safety factors for the different states are calculated. And the table 2, I show you a result of slope stability from cross section 1, 2, and natural terrain. The safety factor is 1.26, and at water saturated terrain is the same. The natural terrain with earthquake and 0.97. That is lower value from safety factors. Natural terrain with additional load 1 to 22. Cross section 3 and 4 is near Paevolu. Natural terrain is 1.31. The water saturated terrain is the same. Natural terrain with earthquake 0.97. Natural terrain with additional water is 1.26. From cross section 5 and 6 natural trends, the safety factor is 1.23. The same is water saturated terrain. For natural terrain with earthquake, the value of safety factor is 1.0. The terrain with additional water is 1.19. Sorry. Conclusion. In the selected same area, a slope section of the Fold and Wozenska mountain, some curated of the engineering geological condition in the periphery of Sofia Kettle have been estimated, which would contribute of the careful assessment when undertaking technogenic intervention in such section. From the performed study and analysis of the slope stability, the following conclusion can be made about the influence of the variation factor of the stability of the study slope. In the natural state, the study terrain of tree analyzing profile is in the stable state. As the coefficient of the safety factor is the range between 1.23 to 1.31, depending on the natural slope and the variation from the ground. The increases of groundwater level has weak effect of the stability of the slope. This also due to the fact that this embankment has a role to retain water in the open channel, which located next door, and to protect neighboring areas from folding. With estimate for maximum earthquake of 9 degree, the stability of the slope decreases to value 0.97 to 1.0, which characterizes its unstable. When reporting the wall at the top of the slope in the amount of the heavy truck, a negative impact is found on the coefficient of stability, which decreases to 1.19 to 1.26, but nevertheless the slope remains stable. The most adverse effect of stability of the study terrain is the seismic impact, as the coefficient stability decreased by 23 to 35% of that the natural state. In the natural state, in case of additional load on the considered slope, the coefficient stability decreases by 3 to 4%. In this case, the main trigger of the occurrence landslide may be the seismic impact, as well as combination of two or more anthropogenic factors. Acknowledgement, this work has been carried out the framework of National Science Program Environment Protective Reduction Risk and Adverse Events and Natural Disaster. Thank you for your attention.
Miroslav, thank you too. We are moving to the next speaker and we are 4 minutes ahead, so please be careful with the time. Next speaker is Professor Sulakov, and he is going to present us something very expected from the seismologists in the region. We will hear a presentation about the earthquake catalog for Bulgaria and adjacent areas since 1981. Dimo, it's your turn. some more seconds to share the presentation and to unmute the microphone.
Okay, do you hear me?
Yes.
Okay,
We
I
hope
had
to
some
see you too.
problems. And
Now it's perfect.
okay, I will present you an earthquake catalog for Bulgaria and adjacent areas since 1981. First of all, I would like to mention that reliable earthquake catalogs are the starting point for many seismological investigation, as well as some geophysical and geological investigations. For example, seismic hazard and risk assessment, structural investigations, and earthquake prediction investigations. It's well known that Bulgaria is an earthquake-prone country. The first well-documented earthquake on the territory is the 1st century before Christ quake occurred in the Black Sea near the town of Kavarna. There are some indications for tsunami generation from earthquakes in this area. Some of the Europeans' strongest earthquake previous century occurred in Bulgaria between 1901 and 1928. There occurred 5 earthquakes with magnitudes around 7. The strongest one was in 1904, well-known Kresna earthquake with magnitude 7.6, which was, and 20 minutes before that earthquake occurred an earthquake with magnitude 6.8. And in 1928, along the Marica Valley, a sequence of 2 destructive earthquakes occurred, and there are many damages in the towns of Plovdiv, Chirpan, and Arhumai. Some words about the seismic networks of Bulgaria. At present, our institute, National Institute of Geophysics, Geodesy and Geography, runs the Bulgarian Seismological Network. The modern network was founded at the end of 1980. At the moment, the institute operates 2 local seismic networks around nuclear power plant Kozloduy and around salt body of Provadia. In 2005, all the stations of the seismic network was upgraded, and now all they are digitized. At the moment, the upgraded Bulgarian Seismological Network consists of National Data Center at the Institute and 25 field stations. The main task for a reliable catalog is harmonization of the catalog concerning the magnitude. The moment magnitude MW is considered to be worldwide seismological community to be the most reliable magnitude scale. That's why we use this magnitude for our catalog. Because up to the 2007, we use duration magnitude, and after that we use magnitude based on P wave magnitudes. We use two relationships to convert these magnitudes to moment magnitudes. The presented catalog was truncated at moment magnitude 3.2. This value is theoretically minimum magnitude of completeness for the whole period and the whole territory, except some parts of Black Sea, for longitude greater than 29 degrees east. Here on this slide you can see epicentral map of the earthquakes in the catalog. The data for the catalogs were collected from the seismological bulletins of Bulgarian Seismological Network for the considered period and for two catalogs, one up to the 1991 and the other up to the 2002. The data in the catalog are unified and standardized in accordance with the requirements, international requirements. The foreshocks and aftershocks and swarm events are identified. Uniform magnitude measure W is estimated for, The catalog, the whole catalog consists of 1,024 events, 655 main events, and 645 events up to longitude 29 degrees east. The earthquakes in the considered region occurred mainly in the earth crust up to 30 kilometers depth. The hypocenters are mainly located in the upper crust up to 20 kilometers, and the maximum density is between 2 and 15 kilometers. A key requirement of any earthquake catalog is to be evaluated the minimum magnitude of completeness. Catalog completeness is defined as magnitude MC, above which is considered to be fully reported and is based on decluster catalog. That means aftershocks, foreshocks, and swarm events excluded from the catalog. The B-value stability approach is applied for analysis of the catalog completeness. The magnitude MC is defined as magnitude at which the following criteria are satisfied. That means the difference between B-value for a given magnitude to be close to an average value for 5 consecutive magnitudes greater than this magnitude. The results show that the catalog could be considered as complete for magnitudes 3.2. Usually, the earthquake process with excluded aftershocks, foreshocks, and swarm events is considered as a Poisson process. We applied two tests for Poisson distribution of the cluster catalog. One of them is the conditional chi-square test, and the other one is Kolmogorov-Smirnov test. The null hypothesis is that earthquake process is a Poisson process. Here you can see the results applying conditional chi-square test.
Dimo, you have 2 more minutes.
Okay, the time period of the catalog is divided in 142 disjoint time intervals with length 100 days. And the hypothesis, Poisson hypothesis, is rejected for the whole catalog. We apply the test for 2 subcatalogs up to the largest event and after that, and for these 2 catalogs, subcatalogs, the Poisson hypothesis failed to reject. You can see here that the mean value of events for 100 days is quite different for the 2 periods. The results for Kolmogorov-Smirnov tests are approximately the same. The null hypothesis is rejected for the whole catalog, while the null hypothesis failed to reject for the 2 subcatalogs. Our main conclusions are that it is compiled unreliable catalog for the time period after 1981. Reported magnitudes for all events have been converted into harmonized moment magnitude scale. The completeness test shows that the catalog is complete for moment magnitudes larger than 3.2. The hypothesis for temporal homogeneous Poisson process for whole catalog is rejected, while it fails to reject for the 2 subcatalogs before and after the strongest event in the region. And acknowledgements. This study was performed in the framework of the National Science Program and environmental program for reduction of risks. I can see here the full name of the program. Okay, thank you for your attention.
Okay, thank you very much. Just to remind, please type your questions in the chat. So we are moving quickly again to the sea. We'll hear about a tsunami scenario. And our next presenter is Luba Dimova. Luba, you are here. Welcome.
Do you hear me?
Yes, we hear you.
Okay, maybe Professor Sulakov should stop share his content.
Yes. It is not.
This is not
my content.
It is Miroslav's content, but
okay,
maybe you can try to share yours. Dimo, mute your microphone, please.
Okay, is it clearly seen now?
Yes, we can see.
Okay, good afternoon, everyone. My name is Luba Dimova, and I work as a research assistant in the Department of Meteorology and Geophysics in Sofia University. So my topic is aggregated tsunami scenario for Karpathos Island, and this is a collaboration between Sofia University and University of Bologna, Italy. So here I prepared a methodology of what we do for the tsunami simulations. First of all, we collect the seismicity and historically documented tsunamis for the region of interest. After that, we select the tsunamigenic source In our case, in this study, this will be an earthquake, seismic source. After that, we have to collect bathymetry and topography data with fine resolution. So we can build the computational grids, which includes the boundary condition. The generation of tsunami is performed using Okada's method. In order to model the generation of tsunami due to an earthquake, the displacement over the fault plane has to be transformed into the formation of the seafloor. Okada methods presents a complete set of solutions for each point source as well as for rectangular fault. So the focal mechanism is one of the most important parameters in this model, which determines the fault geometry. For the propagation and the impact on the coast, we use the model U-boat-Zooft, which is developed at the University of Bologna by the working group of Professor Stefano Tinti. So the model resolves Navier-Stokes equations in approximation of shallow water theory by the finite difference technique through an explicit leapfrog scheme. After that, we built the aggregated scenario, which is all the results obtained for the 3 individual scenarios. We combine them in order to construct the procedure known as aggregated tsunami scenario. And after that, we analyze the output files. So here on this panel, you will see the region of interest, which is the Aegean region. That includes a large part of Greece and Turkey, and obviously it is characterized by high seismic activity. Because in this zone there is a subduction zone, the so-called Hellenic arc, where actually the African plate submerged beneath the Aegean microplate. Karpathos Island is the second largest of the Greek Dodecanese islands, and in particular it is situated in the southern part of the Aegean Sea, near the boundary of tectonic plates and volcanic arcs. So here the seismicity with the black circles, you can see, over 2,500 earthquakes since in the beginning of the last century, and about 49 tsunami which are documented in the Global Historical Tsunami Database. The seismicity is taken, the data, the seismic data is taken from the International Seismological Data Center. So our computational grids are here. All of the tsunami simulations are carried out in 4 grids with different resolution in order to evaluate the maximum wave elevation and the inundation zone. The outer grid, grid 1, includes the eastern part of Crete, the islands of Karpathos and Rhodos, and the eastern Aegean Sea. The smaller grid, grid 2, covers the area of Karpathos Island, and nested 2 grids. We have 2 grids nested in the grid 2, which are grid 3 and grid 4, that are located in the southern part of Karpathos, with focus on the airport, grid 3, and the city of Karpathos, grid 4. The bathymetry and topography data is compiled by different resolution datasets. In this case, we have used GEPCO, SRTM, and EMODNet. You can see some characteristics in this table. The spatial resolution for the outer grid is 500 meters, and for the finest grids is 20 meters. For the calculations, it's good that those total number of nodes is not to be larger than 1 million because of computational time. So our tsunami sources and the initial conditions are presented here. We have selected seismic sources in the vicinity of Karpathos Island, one placed near Crete Island in the Eastern Hellenic Arc, with reference to the 1303 event, where the moment magnitude was estimated to be around 8. Another near the coast of Karpathos, based on the 1948 event, with estimated moment magnitude 7.3. And another one near Rhodos, with magnitude 7.3. For the geometry of the fault, like the length, the width, and the slip over the fault, we have chosen the formulas proposed by Wells and Coppersmith and May and Barroso. And for the focal mechanisms presented by the strike, dip, and strike angle, we have chosen those three papers to be the reference. Why hypothetical for Rhodos? Because in the past there were a lot of, I don't see if, okay. There were a lot of tsunamis in the past here, so we took the maximum magnitude for our event hypothetical, and strike, dip, and rake angle, which will maximize the effects toward the Karpathos Islands. So here is presented the propagation from the Eastern Hellenic arc source. It can be clearly seen that after 12 minutes, the waves reach Karpathos Island. A lot of energy is affecting the southern part of Crete. This small island here, Kassos, is not taken under consideration because of the low population and higher mountains there. So here we can see the propagation for the Karpathos source. This scenario referred to 1948 indicate that in case of tsunami due to this source, the evacuation time for the eastern and the southeastern coastal zone of Karpathos is less than 5 minutes. About the Rhodos, Rhodos source, which is far from the Karpathos Island, we can see that the first positive wave generated by this source reached the eastern part of the island after about 20 minutes. Mainly the radiation pattern here is focused between the eastern part of the island and the southwestern part of Turkey. Here are presented the maximum elevation field for the outer grid 1 and 2, again for the source referred to 1303. This scenario contributes mostly to the southwestern part of the island. The most affected areas from potential tsunami for this source are the city of Arkasa, which is situated something here, if you see my mouse, I guess. City of Arkasa and the airport. Large part of the tsunami energy is concentrated again toward the Crete, where the maximum elevation height reach 5 meters. For the Karpathos source, okay. Karpathos source distributes its maximum energy toward the eastern and southeastern part of the island. Potentially threatened areas are the capital, Karpathos, and some small resorts to the south, like Laki, Kipi Afiarti, in the eastern side of the airport, which is somewhere here. Both of the sources generate maximum elevations around 5 meters, while Rhodos hypothetical scenario has insignificant impact on the coast of Karpathos with positive waves around 2 meters. The model allows us to compute synthetic mareograms, which are the evolution of the tsunami in time. So this figure on the left shows the first 2 hours of the amplitude dynamic of the tsunamis due to the 3 sources. The position of the 5 mareograms is shown on the right, and above it are the names. So for the city of Arcasa and the airport, Eastern Hellenic arc source dominates with long period amplitude between 5 and 10 minutes. Minimum and maximum elevations generated by Karpathos and Rhodos sources for these 2 points vary in the range -1 and +1 meters. For Karpathos North and Karpathos South, the leading first positive wave is induced by Karpathos source, and it is followed by a negative drop around 5 meters, in particular at Mareogram Karpathos, which is confirmed by eyewitnesses during the earthquake from 1948.
Luba, 1 more minute to finish your presentation.
Okay, so the aggregated tsunami scenario is a combination between the outputs from the 3 others. The extreme value reached in every single node of the grid is selected to build those maps. The upper panel illustrates the aggregated maximum water elevation field, zoomed for the grid 3 and 4. The lower panel shows the horizontal particle velocity. Here is the water column on the coastline, which here is plotted over as a layer over Google Earth. Somewhere here are the buildings at the airport, which in case of tsunami, they will be inundated, like 4 meters, as you can see. Again, near Karpathos, the capital, we have also inundations. Another interesting parameter is the maximum momentum flux, which is the most suitable for damage indicator, and also it is useful for engineering applications. And to finish, those are time travel maps where we can see again the propagation in minutes due to the EHA source. In less than 12 minutes, the waves reach the southern part of the island, and from the Rhodos hypothetical source, we have 20 to 28 minutes. So to conclude, we assess the tsunami hazards on the coast of Karpathos by means of an aggregated scenario. The results show that EHA source referred to the 1303 event has a maximum tsunami impact to the southern part of the island. Karpathos source reference event 1948 affects mostly the eastern coastline. The city of Karpathos and the airport are exposed to tsunami inundations, and while the northern part of the island remains undamaged due to the presence of mountains along the coast. So thank you for your attention.
Luba, thank you for your interesting presentation. Now we are moving forward. Our next presentation is about a laboratory experiment with some sedimentary habitats from Sozopol Bay. The presentation is recorded on a video, and the presenter is Stefania Klein. So we are going to watch a video.
Hello, my name is Stefania Klein. I'm a researcher at the Institute of Biodiversity and Ecosystem Research of the Bulgarian Academy of Sciences. I'd like to present the results of our study entitled Effect of Organic Matter Loading on Nutrient and Oxygen Fluxes at the Sediment-Water Interface in Different Sedimentary Habitats in Sozopol Bay. Coastal ecosystems located at the interface of land and sea are home to some of the most diverse marine ecosystems with a variety of habitats and biological communities. At the same time, the coastal zone is densely populated and has been for the entire human history. Many often competing human activities are concentrated there. They often result in increased nutrient inputs to the coastal sea from agriculture, industry, coastal cities, transport. The eutrophication resulting from these inputs and consequent deterioration of water quality are still reported worldwide, despite legislative and management mitigation measures in recent years. Coastal systems being the... I'm a researcher at the Institute. Hello, my name is Stefania Klein. I'm a researcher at the Institute of Biodiversity and Ecosystem Research of the Bulgarian Academy of Sciences. I'd like to present the results of our study entitled Effect of Organic Matter Loading on Nutrient and Oxygen Fluxes at the Sediment-Water Interface in Different Sedimentary Habitats in Sozopol Bay. Coastal ecosystems located at the interface of land and sea are home to some of the most diverse marine ecosystems with a variety of habitats and biological communities. At the same time, the coastal zone is densely populated and has been for the entire human history. Many often competing human activities are concentrated there. They often result in increased nutrient inputs to the coastal sea from agriculture, industry, coastal cities, transport. The eutrophication resulting from these inputs and consequent deterioration of water quality are still reported worldwide, despite legislative and management mitigation measures in recent
Okay,
years.
if there is some problems with the video, we can move forward and to leave this presentation for the last schedule
and or transforming
time slot.
nutrients or recycling them back into the water column and making them available for primary producers. These processes depend on physical, chemical and biological factors, particularly oxygen concentration in bottom waters and advective transport, making the venting. Many often competing human activities are concentrated there. They often result in increased nutrient inputs to the coastal sea from agriculture, industry, coastal cities, transport. The eutrophication resulting from these inputs and consequent deterioration of water quality are still reported worldwide, despite legislative and management mitigation measures in recent years. Coastal systems, being the first to receive anthropogenic nutrient inputs, act as a buffer for the open ocean.
Mr. Tonov, do you agree with the small change in the schedule?
Recycling them back into the water column and making them available for primary producers. These processes depend on physical, chemical and biological factors, particularly oxygen concentration in bottom waters and advective transport, making the venting compartment either a source or a sink for nutrients, depending on the conditions. And
I personally didn't hear any voice.
a release of nutrients from the sediments, for instance, can sometimes lead to secondary benthic-driven eutrophication and worsened water quality. The nutrient fluxes at the sediment-water interface link the benthic and pelagic compartments and are a crucial factor affecting nutrient balance and primary productivity in the water column.
So we can watch it in the YouTube channel and then, yeah.
Silts. However, sandy sediments with their variable topography and sometimes deep pore water penetration can provide conditions for efficient remineralization of organic matter.
Yes, I think it's okay in the YouTube.
The sands are also some of the most common and widely distributed benthic substrates and therefore likely play a significant role in biogeochemical processes. Along the Bulgarian Black Sea coast, there are several studies on sediment water nutrient fluxes. Very high fluxes were, for instance, registered in front of Kamchi River, attributable to riverine inputs, and also in Varna Lake and Varna Bay, especially in summer, enough to support hypereutrophic and eutrophic conditions. However, there are few studies on these processes in the southern Black Sea, where Burgas Bay, the other large bay along Bulgarian coast, is located. Therefore, the current study aimed to quantify the interfacial nutrient fluxes in different sedimentary habitat types in Sozopol Bay and their changes under experimental organic loading through a laboratory experiment. Our study area was Sozopol Bay.
I just pasted the link to YouTube, so I invite you to listen to the presentation in the YouTube channel, and then we will move back here for the next one.
3 seagrass meadows, different soft bottom biotopes, and reefs with macroalgae and black mussels. The area is strongly influenced by different anthropogenic pressures from the town of Sozopol, extensive tourism in summer, and fisheries. 4 stations were selected in the bay, representing different common sedimentary habitats in the area. Station 1 had coarse sandy substrate, Station 2 fine sand, Station 3 fine sand mixed with a little silt with seagrass cover, Station 4 adjacent unvegetated patch with a seagrass meadow with similar structure, similar substrate. 3 replicate undisturbed cores with diameter 10 centimeters were collected at each station by scuba divers and transported to the laboratory. One of the core sediment samples was disturbed during handling and transportation, leaving only 2 for that habitat type. In the laboratory, the samples were placed in a gently aerated aquarium and left to acclimate in near natural conditions for 1 month. Distilled water was added weekly to the aquarium to maintain water level and salinity. After this period, 1 replicate per habitat type was used to measure sediment parameters such as water content and porosity and organic matter content. In the remaining replicates, nutrient and oxygen concentrations were measured in the water layer overlying the sediment surface and in the pore waters within the sediments. And these were the starting conditions of the experiment. Then 1 replicate per habitat type was loaded with 6 grams dried and fine ground green algae deposited on the sediment surface, which is about double the normal surface organic matter in a typical seagrass bed in the study area. Effectively, this simulates organic loading such as might occur after an extreme eutrophication event. The core sand only had 1 replicate left, which was treated with organic matter, and there was no control. The experiment continued for 39 days. After that, the pore water nutrients and oxygen and the sediment parameters in each sample were measured again according to the same protocols, representing the end conditions of the experiment. The measured concentrations were used to calculate the diffusive fluxes at the sediment-water interface according to Fick's first law, corrected with the porosity and tortuosity for the particular sedimentary matrix, and with additional corrections of the specific diffusion coefficients of the solutes for the temperature and salinity during the experiment. The fluxes were expressed in millimoles per meter square per day for the nutrients and milligrams per meter square per day for the oxygen. Positive values corresponded to uptake of a solute by the sediments and negative to release of a solute to the water column. All sediment types were a source of ammonium throughout the experiment. The ammonium fluxes were the highest, dominating the nitrogen exchange at the sediment-water interface. They were also usually considerably higher under organic loading, sometimes increasing tenfold, for example in the fine sand, but they didn't change as much in the sediment from the seagrass bed. On the other hand, all sediment types acted as a sink for nitrates. In most cases, the sediment uptake also increased under organic loading, with the only exception the sediments from the unvegetated patch in the seagrass bed. The greatest changes were observed in the fine sand and the seagrass. The phosphate fluxes were the smallest throughout the experiment and were often even 0. Under organic loading, the fine sand, seagrass and unvegetated patch from the seagrass bed started releasing phosphates to the water column, while the core sand started taking them up. The phosphate fluxes were much smaller overall than those observed in Varna Lake during the summer, where significant stratification and bottom hypoxia induced a release of phosphates from the sediments. During our experiment, no hypoxic conditions were observed in the water layer overlying the sediments, but by the end of the experiment, most sediments had become reduced at depths below 2 centimeters, which could induce a release of phosphates. The smaller phosphorus fluxes could be related to the higher nitrate concentrations in the overlying water, which other studies have found to slow down phosphate release from reduced sediments. The oxygen flux was always directed towards the sediments as expected, and the oxygen consumption increased under organic loading, most notably in fine and coarse sand. This is probably the result of the decomposition of the organic matter and sulfide ions oxidation. The largest difference was observed in the fine sand, which also exhibited the largest difference in nitrogen fluxes under organic loading. By contrast, there was only a small or no change in oxygen fluxes in the sediments from the seagrass bed, both vegetated and unvegetated, possibly because of increased oxygenation of the deeper sediments by the seagrass root system. The exchange of nutrients between sediments and water is a complex phenomenon dependent on physical, chemical, and biological factors such as temperature, dissolved oxygen, redox potential, organism activities, and organic matter. Our results are comparable to other experimental studies that found that benthic nutrient regeneration generally increases with organic loading, and that high organic loading tends to decrease denitrification rates. The observed release of ammonium by the sediments and consumption of nitrates could be related to stimulated reduction of nitrates to ammonium within the sediments in anoxic conditions, which had developed at depths below 2 cm by the end of the experiment in most of our sediment types. The greatest differences in nutrient fluxes induced by organic loading were observed in fine sand, but there were also differences in all sediment types, which has implications for coastal ecosystem resilience under anthropogenic eutrophication. This study also made apparent the high variability typical for coastal sediments even at small scales. There were sometimes considerable differences in fluxes at the start of the experiment between replicates of the same sediment type, for example the seagrass, before any treatment was even applied. This laboratory study had some limitations which could inform future studies. For instance, more replication should be considered to account for natural variability. The two-point study design could be improved by including more intermediary measurements, which could allow us to trace the immediate effects of the organic loading on the different sedimentary habitats. The macrofaunal communities were not considered here, but should be taken into account in the future because their behavior and activities may strongly influence nutrient cycling and fluxes by redistributing organic matter, modifying sediment redox conditions, and creating chemical gradients and interfaces for solid exchange. Dense macrophyte covers such as seagrass beds could also alter the fluxes by capturing nutrients from the water column or from the sediments and by increasing oxygen penetration in the sediments through their root systems. This study also only considered diffusive fluxes across the sediment-water interface, whereas in natural conditions and especially for permeable sandy sediments, advection can also be an important mechanism which should be accounted for in nutrient balance studies. In conclusion, nutrient recycling in the coastal marine sediments represents important ecosystem functions such as nutrient regeneration for primary producers and the regulation of the ability to remove excess nitrogen and phosphorus inputs. By performing them, coastal ecosystems mitigate eutrophication and confer resilience to coastal zones and, by extension, the open ocean. Despite its limited scope, this study adds to the current knowledge of the influence of sediment type on nutrient cycling in the coastal Bulgarian Black Sea and contributes towards our understanding of the role of coastal benthic habitats in water quality regulation. Thank you for your attention. If you have any questions, I'd be happy to answer them.
Here, the presentation which was missed from the first slot, the presentation about Black Sea waves with presenter Vasco Golov. So now it's turn to give the floor to Ms. Petya Ivanova, She's here. Okay, perfect. Go to presenters mode and unmute your microphone. We can hear you.
Let me see, where am I? I can see where am I. Okay. So can you hear me?
Yes, we can hear you.
So
turn on
good
the
afternoon.
presenter.
Good afternoon. If you can you hear me?
Yes, we can. Good afternoon.
So good afternoon. So I am going to present. I am an assistant professor in the Institute for Climate, Atmosphere and Water Research, the Bulgarian Academy of Science. This is a short presentation for the study, which was about landscape assessment of the territory, which was was done as a predefined study for the development of management plan of Vrila Monastery Nature Park. And actually, this is the landscape assessment was part of the bigger picture, which was biodiversity conservation project, and it was with different parts, and landscape assessment was one of the parts as a unique development, as a rapid assessment, which a big territory of area was done for a relatively short time. And it was done by three parts. First was analysis of natural resources, which was assessment of the landscape elements as natural resources like rocks, like forests. Is there any shrubs, open spaces, which are pleasant to see, like meadows, like also is there any aquatic elements? Is there plant or animal species available, which is there cultural or historical landmarks? Is there infrastructural sites or some during the assessment? Is there some kind of pleasant sounds which the evaluators could hear or not? The part B was the analysis of the assessment of the quality of the landscapes, which it was done by the preliminary chosen indicators. The indicators have been developed by the landscape architects, by the group of experienced landscape architects, conservationalists, and the people who are dealing with nature conservation. And they evaluated the picturesque, the natural beauty, the stable. Is the landscape look stable? Is it look unique, or the diversity of landscape? Is it typical? Is it also vulnerability to the landscape, or also it was an important factor, its accessibility? It is not it was not be discussed very in much details, but it was done the ranking of these quality indicators, the results, and finally it was done like a complex landscape assessment of the quality of the landscapes have been observed. And actually, the thing which is have to be mentioned, that the most important factor, it was the quality of the landscape, and the second it was the second factor for its important. It was the from point of view, is it natural, the landscape, or is it was disturbed by the anthropogenic factors? The third factor was the stability. Some kind of, is it really is there some kind of intrusion in the landscapes? The fourth place was the factor of its uniqueness. Is there rare, exotic? The fifth place was the factor of diversity. Is it the landscapes? The sixth place was according to the importance of their importance is given to the factor of vulnerability of the landscapes. Seventh place was given to the accessibility, which is really the seventh place, but it's seen also as an important factor. The last place is given to the typical nature of the landscape of the territory, and it means that the landscape architects and the specialists, they evaluate is it really typical for the area which was considered, which was evaluated. You can see here according to the assessment of these natural resources, actually there is evidence that the territory is a rich variety of perspectives, natural elements, flora, fauna, sounds, and touristic sites, which as follows. Most of the landscapes, almost all the surveyed landscapes, have a rich diversity of perspectives, near, medium, and far, which was really evaluated by the evaluators as a very attractive. It could be said in the beginning that actually the evaluation was done by two parts. One was on site, visiting the territory on site, and the second part was making the photographs, and actually after that it was chosen a number of photographs. For approximately 100 photographs, they were chosen like a 30. So all these results are like a summary of this evaluation. And also the water elements was very valuable, like lakes, river, waterfalls was considered as an essential part of the natural landscapes, which were presented, and they are presented in 62% of the cases. And the rocks and rock formations, which are another important element of the landscape value, again in the big part of the landscapes observed. Of course, there is the territory, it's unique itself, and there is a rich variety of flora, vegetation, forests, shrubs, which are more than 2/3 of the territory. Open spaces, they also have as a diversity landscapes. This is big diversity, so we have presentation of all of these elements. In the majority of the studies landscapes, there were really almost all the territory have a rare and beautiful plant species, and also the fauna was also valuable place. It was like animals which were detected in 65% of the landscapes, and also there were a lot of natural and harmonic sounds which could be listened. It is almost in the whole area. As a tourist infrastructure, it was developed. It was seen that it's quite well presented in the area, which means the roads, paths, like shelters. And from point of view of cultural sites, because this is the area is mostly with the natural beauty, that is a relatively small percent for the cultural sites which have been presented. And finally, as a result, the overall assessment shows that almost all the studies landscape, almost 85%, have really highly picturesque, expressive landscapes, and a lot of almost all of them here, they are really stable because it's really very rich area. They are stable and good, they are preserved, well preserved, and most of them are really have actually high degree of originality and unique. And this is you can see this is the complex assessment with the all with the all ranks which are given, and you can see that really bigger part of the, actually the biggest part of the area have a very high quality of assessment of landscapes, and high, so very high and high. So it's a really very small part of the area which was really affected by the, badly affected by the tourists or infrastructure, and it was really affected like a low quality. And based on this quality of this assessment of the quality which was done for this period under this project, actually it was, the reason was to make a zoning of the part of the territory with the different parts of the area which could be used for different purposes, and for planning for the territory, and it was done like it was used for the recommendations for risk assessments, or for the some of the territory was very vulnerable, the others was more appropriate for the touristic purposes, or for collection and fruits. So it was based on these qualifications, on this quality of the landscapes. It was the zoning of the territory had been made, and the notion, the idea of this renovation of this assessment of this methodology was that actually the knowledge about the quality of the territory, of the natural, in this case it is natural landscapes, should be known in order to be like a prerequisite before further risk assessment to be done, and further in order to collect really solid knowledge, which is done by the multi-purpose team, which is collected experts and also with the opinion of local people on the base of predefined indicators which are important for the specific study, and then it could be used as a methodology for further risk assessment and for the really very good quality management plans. And this is, I would like to have to say the thanks for the team which worked for this project, which is for the bigger picture, for the rapid ecological assessment of the territory, which were completed much more elements, and a rapid landscape assessment was part of this project, which was biodiversity conservation and economic growth, and which was done for the first time, manageable to be done by the relatively small part. The group of people which work on the terrain was 3 people. It was 1 landscape architect, 1 forester, and 1 sociologist. But it was the whole process was very participative, collaborative process, and with co-creation process. So it was really very good methodology developed under this project. And thank you for your attention. It was relatively shorter than 15 minutes, but if you have some questions, I would like to answer. So thank you for your attention.
Thank you very much for your presentation. If anybody has questions, please type them in the chat. Now we will hear the last presentation, which is about the Black Sea waves for the last 40 years. So I'm giving the floor to Mr. Golubov. He's here.
Okay, I'm here. Can you hear me?
Yes, we can. Welcome. Share your presentation, please.
Yes, a moment. So my talk is about the Western Black Sea waves. the waves influencing the Bulgarian coast during the period 1980 until now, 2020. And the study is based on ERA 5. I will comment a little bit later what is ERA 5. So the outline is goals of the study, methods and data, results and conclusion. Speaking about the climate of the Black Sea waves, there are a number of studies. This is not the first study, there are a lot of studies. Some of the first are the studies of Vouchev from the Institute of Oceanology, Akpinar from Turkey, Rusu from Romania, and others. And all the studies are based mainly on wave modeling, using different wave models. And these models need atmospheric data for the wind. And in all of these studies, the atmospheric data is coming from the so-called atmospheric reanalysis data, such as ERA 40, ERA interim, and CEP reanalysis project, and CEP reanalysis 2, CFSR, or downscaling of reanalysis, such as REMO. And the author of the present paper used ERA CLIM for such a study. This is the longest available European reanalysis, 110 years European climate reanalysis, and the results are published in this paper written here. But the present work is based on the latest European effort, which is called ERA 5. And the advantage of ERA 5 is that it's available for now from 1979 to 2020. So it's possible to see the wave climate for the most recent decade. And also a great advantage is that it will be prolonged soon from 1950 to 2020. And this reanalysis is with much higher spatial and temporal resolution than the previous reanalysis. The study is based on the use of the SWAN wave model. SWAN means simulating waves near shore. This is a numerical model modeling the sea waves developed by the Technical University of Delft, Netherlands. And I'm running two simulations. The first simulation covers the entire Black Sea area with a spatial resolution of 1/10 degree. So this is 6 minutes. And the second area, you see it here, the boundary of the second computational domain is the yellow line. It covers the western Black Sea coast and the entire coastline of Bulgaria, of course. The spatial resolution for this simulation is 2 minutes or 1/30th of degree. So I computed the entire period 1979 to 2020, obtaining an output each 3 hours, for each 3 hours for the entire period. And after that, the data was processed. And in the study, I used several proxies of the storminess. These are indicators of the storms, of the storm climate. And some of these are the annual maximum significant wave height for the nested domain, the number of the storms per year, using two different thresholds for the storm. One is 2.5 meters, or wave force 5. And the second threshold is for the more significant waves, 4 meters or above. Another proxy that I use is the number of the storms Yeah. Excuse me. And in order to characterize the energy of the storms, the total wave energy flux was used. It is calculated using this formula. So the energy depends on the period of waves, the so-called energy period, and the significant wave height. And energy is calculated only when the wave power flux is only when the significant wave heights are above 2.5 meters, and I denote it as E25, or above 4 meters, or E40, and also other storm proxies such as the storm power index of the authors Dolan and Davis. So some of the results. So first of all, you see on the left here the number of the storms. If we define a storm, an event for which the waves reach a significant wave height of 2.5 meters. Here the results are for 2 points at the Bulgarian coast, Ahtopol and Chabua. And so the outcome is that the trends are not statistically significant for this period. On the next picture, on the right, we see the number of the storms. If we define a storm, an event with significant wave height above 4 meters, and again, we found that there are no statistically significant trends. So speaking about the energy of the storms, the energy is obtained for the entire year. So we see here the annual storm energy. And if we use a threshold of 2.5 meters, again, there are no statistically significant trends. And if we define a threshold of 4 meters for the location Shabua, again, there is no statistically significant trend. And we see some negative trend for Ahtopol. However, it also does not fulfill the test of statistical significance of Mann and Kendall. And if we calculate for the entire area, for the entire computational domain, again, the storm energy does not show any statistical significant trends. The same goes for the annual maximum wave height. So, conclusions. First of all, this study in general confirms the conclusions of other authors that for the Western Black Sea coast, the trends in the wave climate are not statistically significant recently. But for the first time, ERA 5 was used to do such a study. There are hints of some positive trends, but to be clarified, positive and negative, but to be clarified, the study will be extended soon when the ERA 5 becomes available for the entire period from 1950. So, thank you. I think that that's enough.
Thank you very much, Mr. Golubov. Thank you, all of you. Because we had one extra presentation, our time is almost finished. In the chat room, there is one question. It is to Professor Sulakov. And the question is, if the catalog is published, please provide us information how to find it. So I will ask Professor Sulakov to give us a link or something useful to be able to download the catalog and to use it.
Okay, the catalog is published on the site of the institute. You can download from there.
Okay, thank you very much. You can just paste the link in the chat, in the YouTube channel. But
Okay,
yes,
one moment, please.
Okay. Thank you very much. It was very fruitful session. Thank you all the presenters. We heard very interesting topics, very interesting talks. I wish you a successful day tomorrow, which is the second day on the conference, and the workshop, which will be after the conference. Again, thank you very much to all of the presenters. Goodbye from me.
Thank you.
Thank you. Have a nice evening.
Thank you, everybody. Have a nice evening for everybody.